Hello, good evening all. Are you able to hear me?
Yeah, good evening, madam.
Yes.
Yeah.
Good evening.
Yes, good evening. So did you all get the announcement for mock
Yes, ma'am.
revision session?
Yes, ma'am. Could you please explain that, ma'am, how it will be distributed?
Okay, so tomorrow the mock will be released, and Thursday evening you have a session for mock revision.
Right, ma'am.
As usual, the session that used to happen, that will happen. But let's say many of you will have various doubts in between. Like once, like somebody is explaining a particular question, then a lot of discussion, if it happens on a particular question, then it gets read a lot, right? So if you have a doubt in like particular topics from specific weeks, like we are going to have 3 breakout rooms. So in the first breakout room, questions from week 1 to 8 will be discussed. Whatever is there in mock, questions on that will be discussed. One playlist will be provided to you where the solutions are already recorded. You can watch it, and if you have doubt in that or you want to know something more, you can stay in that breakout room to get your doubts clear. So for week 1 to 8, you have one breakout room. Week estimation part, you have one breakout room, and hypothesis testing, you have one breakout room. Okay, and the main session will happen as usual.
Ma'am, whether recordings will be available for entire session, like the main session as well as breakout sessions?
So main session will be live streamed.
Okay, and other sessions, ma'am, those will not...
No, those will not be live streamed.
But all running concurrently, is it?
Sorry, yes.
All the breakout sessions are running concurrently.
Yes.
So that means...
What about these breakout sessions? Where do we get?
Ma'am, is it possible to record them also, ma'am, so that we can watch it later on?
Yeah, that's a good idea. Because everyone has 1/3 of the chance to see anything. No, 1/4 of the chance, not even
1/4 of the chance, yes.
So, okay, if let's say there are some 10 problems in mock, okay, let's say there are 10 problems. In the main session recording, the session is happening as usual as it happens, okay. But let's say out of those 10 questions, some person, let's say, have only the doubt in only 2 problems from one particular topic or 2 particular topic. So the person can go to that breakout room and they can get their doubts cleared. If they have difficulty in understanding the way it is solved, the recording is available for each of the solution. For each of the question, the solution recording is available. You can watch it, and whatever doubt you have from the recording or in general, you can get it cleared in the breakout room.
Ma'am, unless it is listed as a scheduled event in the calendar, we will not be getting the link, no?
Which link?
The breakout sessions are not scheduled in the calendar.
The session is scheduled in the calendar.
No.
Yes, it is scheduled.
He's saying the main session is scheduled. What about breakout sessions? That's what he's asking.
Yeah.
That will be created there only.
Okay.
Yeah.
That links will be available in the calendar?
Not in the calendar. Once you join the session, you can go to the breakout room, whichever breakout room you want to go in.
Yeah, but we are asking the
session.
The recorded session.
Ma'am, could you please repeat, ma'am, once again? I joined just 2 minutes ago, ma'am. I was in the middle of the...
Me also not getting what is this breakout rooms, how to join into the room.
I'm not getting.
So this main session, right? Main session will happen as usual. And once you join the main session, there will be options to go into the breakout rooms if you want to go. Okay.
Ma'am, is there any link provided for that, ma'am?
That will be provided in the main session itself.
Oh,
when is this? There will be options to go in the breakout room from the main session.
You will get it there. So like once you join that session, no, it will be there. You can go in.
Ma'am, the link is not available, no, ma'am.
The link will not be available here. Whatever link that is there for the mock session, you will have to join that session itself first. Later you will see, once you join that session, you will see the breakout rooms there. So if you want to go to some breakout room, you can just go. Okay.
Ma'am, it is not available in the calendar also, ma'am.
No, calendar, the main session link will be available. It is on Thursday.
Ma'am, can you share that link here, please? You can
You
just take
will
out.
see the option in the
Calendar in
Zoom.
the, it is
Join
there
the
in
breakout room.
it is there in the calendar.
But you are telling this breakout room sessions are pre-recorded, right?
No. It is not pre-recorded. Those are not pre-recorded.
Ma'am, again, it is a live session, ma'am.
It is a live session.
Okay. So I want to join there because we get in-depth this one. So can you please help me out how to do that?
But at that time we will miss now this live session, main session we will miss, right? During that time.
Yeah, so either you can do the breakout session, room session or the main
Because
session.
breakout room sessions, it is like chapter wise, like week wise, where we can get in-depth this one, no, ma'am. Actually, like
Yeah, like if you have more
complete,
doubts,
a complete revision kind, the brush up kind we get. So only I was
the
thinking.
questions will be from mock itself, but the topics that come there in the questions, if you want to know something more,
Oh,
it can
But
be
if you arrange separately, that would be much better now than this. We can attend both sessions.
Ma'am, if you can arrange to record that one and post
okay.
it.
We
put
will
it in
check
the
if it is can be recorded, we will do it.
Yeah, that would be the better thing because we are not losing anything. And anyone who is interested, we can get over there.
Yes.
But most of,
No, the mock has not been released. It will be released tomorrow.
okay.
Yeah.
Thank you.
Maybe start the session.
Yes, we'll start the session.
Ma'am, are you taking the doubts right now?
So today's revision session, first we will just go through quickly all the topics that we have, and then
Yes,
we'll
ma'am.
yes, ma'am. First, you clear like all topics we'll discuss,
Yes, ma'am.
ma'am.
First
In
topic, go to
in the
the
beginning,
topics.
if people will ask doubt, no, ma'am, we will get disturbed. Actually, like the flow will get disturbed. So doubt session we can keep after the like completion of a particular topic. That will be more helpful, ma'am.
so like for each week we already keep one session.
Yes, ma'am. Yeah.
Like we already have all this. So this
Yeah.
will be a quick revision, not
Yes,
very
ma'am.
in depth. Okay,
Yeah,
just all
yes,
the
ma'am.
topics that is there.
Yes,
Because
ma'am.
every week you already have those recordings. If you are
Yes, ma'am.
interested, you can watch those recordings. Okay.
Okay.
That's
Ma'am,
important.
the end term, like questions will be same as most similar to the mock.
Yeah, like that. The portions will be similar. I won't say almost similar, but yeah, kind of.
Can you give an estimate around the number of
You get
questions?
most of the similar questions.
Number of like it will be almost equal to what you see in mock. Number of questions also. Yeah. Week 12 graded assignment PDF is not there yet. Okay, week 12 graded assignment. Okay, let me check. If it is not there, we'll upload it after the session.
Ma'am, we are starting from week 8, right?
We're starting not from week 8, we are starting from week 9.
Okay. Ma'am, do we have a place where we get answers to all the practice questions or activities questions?
Sorry, can you repeat?
Like I know about the practice assignment. And do we have a place where we get all the activity question solutions?
No, activity question solution, no, you don't get. But in this course, you can definitely find all of it.
Just search on
Course.
yes course.
Okay. I will try.
Mock for income is not released yet, right?
It will be released tomorrow.
Okay.
Madam, where shall I find the quiz 2 solutions, detailed solutions?
It is not shared. Which solutions are not shared. Yeah. You will have to try it on your own. All right, so let's start from estimation. Since majority of the portion is going to come from estimation and hypothesis testing, we'll discuss parameter estimation and hypothesis testing.
Yes, ma'am. Facing a lot of issue in Bayesian.
Bayesian estimation. Okay. Just give me a minute. It is no. Okay. Oh wait, I'll open this again.
Ma'am, are we covering all the 4 weeks today itself, or like half the session?
The revision is going to be quick. Like you already have a detailed explanation for each week in the live session, right? Like every week session, whatever we do, the detailed.
That's my query, because like I have taught specifically in week 11 and 12.
Yeah, we are going to cover it. So it should like the quick revision should be done in 1 hour, and then we'll look at the questions.
Okay, ma'am. Thank you.
Ma'am left.
Oh, sorry. No, I'm there. It's taking time. Let's do it here. Something. Okay. First, we'll look at parameter estimation. So what exactly are we doing there? We are considering few samples, NIID samples, X1, X2, up to Xn. We have NIID samples from some distribution X. It's not working. Okay, so what we're saying is, let's say we have NIID samples from some random variable X that has the distribution, that has some distribution, and it has few parameters. Let's say the parameter is denoted as theta 1, theta 2. Can you mute yourself? Is that? Yeah. So the parameter is theta 1, theta 2, theta 3, and so on. It can have many parameters, right? Let's say if we write X is a Bernoulli distribution, how many parameters does it have? It has one parameter, that is P. If I write X to be binomial random variable, right? How many parameters does it have?
1.
2. Have N and P, right? Now, if I write Poisson random variable,
1.
it has one parameter. So on. So let's say the samples are coming from some distributions, and those distribution will have some parameters. Now what we want to do is, let's say we don't know what exactly this parameter is. We just know this is the distribution that we have, but we don't know what are the parameters involved there. Now we want to estimate those parameters. Okay. To estimate those parameters, let's say X has the parameter theta. Okay. The parameter is theta. This is a parameter. and we want to estimate this parameter. Okay, so the estimator, this is our estimator. Estimator is denoted as theta hat. So this is just a way of notation. So we are saying theta is our parameter and we want to estimate this theta, and the estimator is going to be theta hat. Okay. And theta hat can be function of NIID samples. It can be any function. It can be any function of NIID samples. So you can write theta hat to be a function of x1, x2 up to xn. So first thing here is, what is our is theta hat a random variable or a constant? What it is going to be?
RV, random variable.
Random variable.
Theta hat is a random
It is a
variable.
random variable.
So theta hat is a random variable because it is a function of your NIID sample. So theta hat is your random variable and theta is your parameter, right? So is theta constant or a random variable?
Constant.
It is a constant. Okay. Now from here, let's look at here only. We had two different approaches to estimate a parameter. One is frequentist approach. Okay. And other is Bayesian approach.
These approaches are used to find parameters, right, ma?
These are, yeah, estimate the parameter. You want to estimate the parameter. So basically in both of these cases, you are going, what you are doing is you are designing the estimator. Okay. For your parameter, you are designing your estimator. So what happens in the frequentist, the difference there is, like in case of frequentist approach, we say that this parameter theta, this parameter theta is a constant, unknown constant, right? This is an unknown constant. Fixed but unknown constant. But in case of Bayesian estimator, we say this theta parameter, this parameter theta is not a constant, it's no more a constant, it is a random variable. So that is the only difference between these two. Now, when we talk about the frequentist approach of design of estimator, we have two different, we have studied two different approaches. One is method of moments. One is method of moments. And other is maximum likelihood. Other is maximum likelihood. Okay. And the Bayesian approach is we'll study next. So first we are going to study this frequentist approach. So what all we have seen in this? So we have a theta that we call it as parameter. We have theta hat that is an estimator of theta, right? We define an error term.
Connect you, charge you.
Yeah. Now we define an error term. What is error? Error is defined as the difference between this, so theta hat of x1, x2 up to xn minus of theta. So this is how we define error to be. And we want this error to be as low as possible, as less as possible. What we want is, what we're interested in is probability that your mod of error, this error, if you take any small delta, this should approach to 0. So basically, your error should converge to 0. Probability of your this error term should converge to 0. If you want to see more on the error, you can look at the activity practice session. Activity practice session for week 10. Okay. Sorry, it is week 9. There, it is explained in detail why we want this error to be converged to 0. So after we looked at the error term, what we define what is error, that is difference of this theta hat and theta. Then we define something called bias of an estimator. Since you have an estimator theta hat, you want to see how much bias your estimator is. So how do you check the bias of an estimator? So you have the samples x1, x2 up to xn coming from IIDX, right? It has some parameter theta. It has some parameter theta, and let's say the estimator is theta hat. Now we define the bias of an estimator. So we define it, denote it as bias of theta hat of the parameter theta. It is equal to expected value of theta hat minus theta. Basically, what is the theta hat minus theta?
It must be 0.
This is error, right? We defined. Defined, this is error. So basically, bias is expected value of error. Now, this is expected value of theta hat minus theta. You know that theta hat is a random variable, correct? And theta is a constant. So this can be written as expected value of theta hat minus expected value of theta. Minus expected value of theta. So what is expected value of theta? Theta, not 0.
Sorry.
Yeah. So since theta is a constant, expected value of theta is going to be theta. Now, when do we say to check whether your estimated is bias or not, we check that if bias is equal to 0. Sorry, this is not theta. We check if bias equal to 0. And when will bias become 0?
When expectation value of
Yes, the bias will become 0 when the expected value of theta hat
equals to the constant
must be equal to the parameter. Right? So whenever it happens, it will say that our estimator is unbiased. We say this is unbiased. Okay. And okay, so whenever a question comes, like you have an estimator, you want to check whether the estimator is biased or not, you have to check whether expected value of the estimator is coming out to be same as the parameter. If it happens, then we say it is unbiased. If it doesn't happen, we say it is biased.
Okay. Ma'am, bias is a expected value of error.
Expected value of error. This theta hat minus theta, we defined it as error, right? Theta hat minus theta. This is also called as expected value of error. Okay. Now, next we have risk of an estimator. Risk of an estimator. So again, we have NIID samples coming from the distribution X, which has parameter theta, and the estimator of this parameter theta is, let's say, theta hat. Okay. Then the way we defined the risk of theta hat, this is equal to expected value of error square, right? Theta hat minus theta whole square. This is also called square error risk. So the way we define risk of an estimator is, it is expected value of square of error. Okay.
MSC, ma'am.
Sorry.
MSC.
Not mean square error, it is square error.
Okay.
Okay.
It's
So
just the square of error, right?
yeah, it is just square of error, expected value of square of error. So yeah, basically mean square error itself, the same thing. It is also called mean square error. We can write it as, this is mean square error. Now, it is possible that even though like you have an estimator and you would want your estimator to be unbiased, right? You won't want the estimator to be biased, right? So even though your estimator is unbiased, like we should check that the risk should be less. Now there is something called variance of an estimator. Variance of an estimator. So you know that theta hat is an estimator and it is a random variable. Okay. So if you have to find the variance of a random variable, how do you find it?
E of x square minus
expected value of x square minus expected value of x whole square. Same thing we will do here because theta hat is a random variable. So this become expected value of theta hat square minus expected value of theta whole square, right? And this is going to be variance of your estimator, and we would want our variance to be less, right? We want this variance to be low. This is variance of estimator. But if we have to find the variance of error, how is error defined? It is defined as theta hat minus theta. Okay. Now, variance of error, this is going to be variance of theta hat minus theta, right?
Yes.
Now, again, can we use the property of variance here?
Yes.
We can use, because this theta hat is a random variable and this theta is a parameter. Variance of x plus c, what do you get? Variance.
Variance of x. Zero. The constant part will be zero.
Yes, it becomes variance of x. So here it will just be variance of theta hat. Okay. So variance of error is same as variance of estimator. Now you have something called bias variance trade-off.
Ma'am, in the fourth formula, variance of theta hat, it is E theta hat square and E theta hat whole square.
Sorry, you're talking about variance of error? Oh, sorry, it is E theta hat. Right.
Okay.
This only, right?
Yeah.
Thanks. Yeah, I missed that. So we have bias variance trade-off. And it is given by risk equal bias square plus variance. Bias square plus variance. So if you know the variance of estimator or the risk of estimator,
Is it
anything that you,
variance of, sorry, ma'am, is it variance of theta hat or variance of error?
this is theta hat.
Okay, thank you.
Okay, so risk, wait. So wait. So,
Variance of what, ma'am?
sorry. Yeah, wait. I will write it down properly. So we just wrote risk equal bias square plus variance, right? What is your risk? How did you define your risk? We defined it as expected value of theta hat minus theta whole square. Okay. So risk is expected value of theta hat minus theta whole square. Now this can be written as the bias of an estimator, that is given by expected value of theta hat minus theta whole square, because risk equal bias square. So this square plus variance of an estimator. Oh, thing. This is wait.
Hello.
Yeah.
Maybe your voice was not audible.
Yeah, right.
Ma'am, risk will be bias plus variance, right?
Bias square plus variance.
Oh, is it? Okay.
Yeah, bias square. This is bias square, no?
Variance can again be written as expected value of theta cap minus expected of theta whole square, right?
Yeah, right. So since okay, this can be written as expected value of the random variable theta hat minus its expected value whole square.
Why whole square, ma'am?
What is the formula for variance?
Expected value of theta hat minus expected value. Sorry, theta.
Like in general, if you have to find the variance of a random variable x, how is it defined?
Theta hat square.
Expected value of expected value of
x minus expected value of x whole square.
Basically expected value of x. It is expected value of x minus its expectation. Let's denote it as mu. This whole square. This is how you define the variance, right?
Yes.
Yes.
So this is our bias variance trade-off. Can you mute? Is there? Okay. Next we will see the design of estimator.
Excuse me, ma'am.
Uh-huh.
Ma'am, for the previous equation, can you tell us like what will be the simplified end result for this?
Simplified end result. Okay. So we know risk equal bias square plus variance. Risk is defined as expected value of theta hat minus theta whole square. Right? So,
Yes.
Okay. The way you can write it as, you can simplify it, but you can remember it this way. So risk was expected value of theta hat minus theta whole square, right? And we know this theta hat minus theta is a random variable, correct?
Yes, ma'am.
Let's denote it as y. Okay. Expected value of y square can be written as expected value of y whole square plus variance of y, right? This is right, no?
Yes.
Now,
Yes.
y is theta hat minus theta. Substitute it here.
So why have we written expected value of y square to be equal to expected value?
Okay. So variance of a random variable x is given as
EX square.
EX square
Yeah.
Minus EX whole
Minus
square.
EX का whole square.
Yeah. From there it is coming.
Okay, ma'am.
Yeah. Okay. Now you substitute just theta hat minus theta in place of y. Okay. So this becomes, this you know is risk, and this term becomes expected value of theta hat minus theta whole square. And we know expected value of theta hat minus theta is bias, right?
Yes.
This is called bias. And you are squaring this, so it becomes bias square. Correct?
Yes.
And variance of y. So the way variance, how do we define a variance of a random variable? We define variance of x to be expected value of x minus expected value of x. I'll write it there. It's not working properly.
Ma'am, your screen is not visible.
Yes. Is it visible now? This one is visible?
Yes. Yes.
I'll write it here.
Ma'am, can you go on a previous screen for a second?
Sorry.
On the previous screen.
Yeah, there I'm not able to write properly.
I just not.
Okay, fine. Yeah. Right, this is how we define variance. Variance of x is expected value of x minus expected value of x whole square. Same thing we will do here. So y is a random variable. We'll write expected value of theta hat minus theta and you will get it as
Ma'am, can we do this later? Because we are missing important things in time.
yes, we can do it later.
Because still the very most of the important, all the important things are left.
Right.
After it,
Yes, ma'am.
we have another session, so we cannot extend this session.
You have session from 8?
Yeah.
Yes, ma'am.
Yes, ma'am.
Okay, so let's short. Yeah, anything in detail if you want. Already each week kind of revision is available. You can go and watch it, okay?
Yeah.
Can we solve some problems or one problem on bias risk?
Yes, ma'am.
Okay.
It will be more clear.
Very helpful.
Yes.
Yes, ma'am, the kind of questions that might be there in the paper.
Okay.
No, ma'am. First, cover all the topics, then solve the questions. Yes, ma'am. Please.
Yes,
Because
ma'am. We'll cover all the topics first, ma'am.
Yeah, because I'm expecting at least Bayesian estimation till 8, ma'am.
Yeah, mainly 3 estimated
And
standard
we have
deviation.
till
Okay, just wait on. Okay, hold on. So I am going to do only the theory part today. Okay. The problem part we can do it on Thursday session. All right.
That's great, ma'am.
So let's see. Method of
So ma'am, on Thursday we'll be solving only problems.
Mock problem is there.
Mock problem, other problem if you want, that also can be discussed. Okay.
Okay, ma'am. Thank you.
Method of moments. Now what we do, like how do we design estimator using method of moment is, like we define,
Find the
we have a
expected
random
and then
variable.
equate to n.
Yeah, we have random sample x1, x2 up to xn. They all are coming from some IID x. Okay. Coming from some IID x. And it has some parameter theta that you want to estimate. Let's denote this as theta hat. This is your estimator. Now, the estimator that we design is this you denote as mk of x1, x2 up to xn. Okay. This is what method of moment estimator looks like. And it is given by sum over xi to the power k 1 by n, where I will vary from 1 to n. This is our method of moment estimator. Now let's say if you have just one sample, like if you have to find the first moment.
Why we are getting x to the power k over here?
Sorry?
How we are getting xi to the power k?
This is how you define the method of moment estimator. Like if we have to find the first moment from here, what it is going to be? Like first moment as in your m1 basically, k to be 1 here. Okay. So this k here will give you different moments. So if we take the first moment, so basically we'll put k to be 1 and you will get sample mean, right? X bar. If we have to find the second moment, you will do x square here, right? So it will become x1 square plus x2 square plus up to xn square divided by n. This way we find different moments of the random variable.
Ma'am, in sums, do we also find the second moment to get the moment of, in problem sums, do we also find the second moment to get the
Okay,
method
so
of moments estimator?
I think all the problems we have seen is just for one
Sample mean,
estimator,
yeah, yeah.
one estimator. So like we will not ask you basically for two random
Go
like
to the second moment.
second moment, because we have not given you in any of the problems in the lectures or in the
Not in
assignments.
detail, it's explained.
Yeah.
Means,
So okay.
okay,
Basic, what we are doing here is like we have one estimate, one parameter. Let's say we have one parameter, and we want to estimate those parameter, and we are trying to design that. So using method of moment, what we do is, let's say if we have one parameter, then we use our first moment to calculate, to find that estimator. Now let's say if we had some two parameters, then we would have used the second moment also. Right? Like in case of normal distribution, you must have seen that we have two parameters, mu and sigma square, and we want to estimate both of these parameters. So first moment we can easily, using first moment, we can estimate our mu, but this but to find the second parameter, that is like estimated for the parameter sigma square, we will have to find our second moment and use the first moment there to get the estimator for sigma square.
so ma'am, number of parameters will give you the number of moments. Like
Yes.
okay.
Yeah.
Ma'am, but we should not expect this like
Second moment, yeah, you should not expect. Yeah.
Okay.
parameter estimator in the like. Okay.
Yeah, you should not expect two moments to find two moments.
Yes, ma'am.
Okay. So what we say is distribution moment. Distribution moment is what? Like you have a random variable. Okay. Like let's say the sample is coming from let's say geometric P. Okay. Now what is the distribution moment? What is the first moment? Basically, first moment gives you expectation. Right?
Expected value.
So this first distribution moment is going to be fixed. This is fixed, right? This P is unknown, but constant. It is fixed. But the sample moment that you will find, right? The sample
It's a random
moment,
variable.
it is going to be a random variable. If you have one parameter, you will have to just find one sample moment. If you have two parameter, you first find your first moment and then use the second moment to find the other parameter estimator. Okay. We will restrict ourselves to the first moment. Let's look at few examples here. So let's say we have an exponential distribution. Let's say the samples x1, x2 up to xn, they are coming from Poisson distribution. Just give me a minute. I will take a fresh page and do it. It's not able to write it properly. Just give me 1 minute, okay? Okay. Let's take the problem from method of moment. So let's say the first example is the samples x1, x2 up to xn. They are coming from a Poisson random variable with parameter lambda. Now again here we have one parameter. Okay. So what do? We find the first sample moment, right? And it is given by sample mean. So
Yeah.
M1, it is sample mean, right? X1 plus X2 plus Xn by N. This is your M1. And what we will do is we will equate this sample, first sample moment using the distribution moment. So this, you know that expected value of X, expected value is lambda. So we will equate this to lambda, right? So the method of moment estimate of this parameter lambda is going to be sample mean. Similarly, let's say if they are coming from, in place of Poisson random variable, it is coming from exponential random variable.
That's it.
Yeah, that's it we do. What we do is, so distribution moment is what? Lambda.
Yeah.
Correct?
Yeah, I got it, ma'am. I got it. I got it, ma'am.
You got it, no?
Yeah.
That's it. Is there nothing else? Method of moment is kind of very easy. Now, if let's say the samples are coming from exponential random exponential distribution with parameter lambda, what is its expected value?
Now 1 by lambda.
1 by lambda, right? And M1, now we will equate this 1 by lambda by M1. Okay. Because 1 by lambda, expected value is the first moment, and the first sample moment is given as sample mean. So from there, we'll just find lambda, and lambda is going to be 1 upon sample moment, first sample moment. And this is what? Reciprocal of your sample mean. And this becomes n upon x1 plus x2 plus up to xn, right?
Ma'am, this 1 by lambda, where it came from?
When the samples are coming from exponential random variable.
Okay, exponential. Because in Poisson, it's only lambda. So I thought you are continuing the same distribution.
No. Now the samples are coming from exponential random variable.
Okay.
So can we always say that M1 first method of moment for any distribution would be the mean?
Yeah, like if you have to, okay, see, if you have only one parameter in your distribution, what you're going to do is you find first the expected value, the distribution moment, first distribution moment, that is the expected value. Okay. These are the known distribution. So we know, let's say in the first case, it was a Poisson distribution with parameter lambda. We knew that if it is the Poisson distribution, its expected value will be given by lambda. Okay. But in case the distribution was not given to you as like Poisson exponential or geometric, whatever. If it was some random variable with some distribution function, then you will have to find the expected value, right? You find the expected value and then you equate that expected value by your sample mean, as we have done here. So in this case, we already knew what our first distribution moment was, what was our expectation was. We equated that expectation by our first sample moment.
So unknown distribution for the parameter for the unknown distribution, the expected value can be equal to moment, first moment, right?
Your voice is not very clear.
What I was saying is for the unknown distribution. Is it clear now?
It is clear.
For the unknown distribution, so here we know that first one is Poisson and second one exponential. In case of unknown distribution, we have the single parameter. So that parameter's expected value would be M1, right? So M1 will be equal to the parameter. Am I right now?
Not able to get you. You are talking about in general.
Yes, ma'am. In general, I'm talking the first
Okay.
moment can
Let's say the distribution of x is given as x1. Let's say it is taking the value x1, x2, x3, x4 with some distribution fx. Okay, and it's going to be fx of x1, fx of x2, fx of x3, and so on. Now, how do you find its expectation? You do x1 times fx of x1 plus x2 times fx of x2. All that you do, and you find your expectation. Let's say expectation came out to be some constant number. Let's say it came out to
K.
Let's say it came out to be k. Now, what you will do is whatever samples you have observed, from there you find your sample mean and you equate this to k.
You mean to say here we just have to add up all these values, right?
Sorry.
So here sample mean we add up all. You mean to say x1 plus M1 should be equal to k, right?
Yeah, you will have to equate your M1 to be equal to k. This can be anything. It will be since all this is going to be in terms of p, it is going to have some probability. You will have some expression in p, and from there basically you will have to find your p. Or let's say if you denote it in terms of theta, then it will have theta. Anything.
But since you mentioned me, I was thinking we just have to use it. Use a normal usual addition x1 plus x2 plus x3 plus x4 by 4, right? Is that proper?
And we can also remember these estimators.
Which estimators?
These general estimators of Poisson like these estimators.
Yeah, you can remember it. Like if it is a Poisson method of moment estimator is sample mean. If it is a exponential, it is going to come out to be reciprocal of sample mean, all that. It's easy to remember all this, but it comes only if you solve a lot of problems. Otherwise, if you know the method, that is better.
Okay.
Then you can do anything.
So, ma'am, one thing here. So M1, this is every time. So we need to find the average, right? The mean, like
mean.
X1. Yeah, every time. That is the first
sample moment.
First sample moment.
So first sample moment is basically your expected value of x. Second sample moment is expected value of x square. Okay, this way you find it.
But we don't know. But we don't need expected value of.
You don't need this because I'm skipping here the sec2 estimator, 2 parameter part. That is why we don't need expected value of x square.
Okay. No, but if in case if we are get to find
in case
expected value of x square.
Yeah, in case okay.
Ma'am had told already.
I had told already, but let's see. Okay.
Okay, but still.
So let's say these samples are coming from a normal distribution with mean, mu, variance, sigma square. Okay. First, I want to find the now what is mu? Mu is expected value, and sigma square is this variance. So the distribution first is expected value is what? This is mu, and this is same as we will equate this as M1. Okay, so what we got? We got mu to be x bar. So mu hat with method of moment estimate is going to be sample mean. Now we want to find the estimate for this sigma square variance, right? We want to find the estimator for the variance. Now here we will have to go for the second moment. So now we will find expected value of x square. So this is what? This is expected value of x. Right? Now expected value of x square you will find as this we write as what? Expected value of x whole square plus variance of x, correct? And expected value of x square is mu square. Variance
Mu
of
square.
x is
Sigma
sigma
square.
square. Okay. And this is R. Now we equate this expected
M2.
value of x square by M2. So M2 is what? M2 is now basically a mu square plus sigma square. And since we have already found this estimated for this parameter mu, that was M1, we can write this as M2 equals M1 square plus sigma square.
Okay.
Okay. So what is going to be the method of moment estimator of sigma? So
Sigma will be
this is going
2
to be
minus
square root of M2 minus M1 square.
yes,
square
square
plus
root of M2 minus
M1 square.
We know M2,
Okay.
we know M1. So M2 is what? M2 is going to be x1 square plus x2 square plus
Till
up to
xn square.
xn square by n. And M1 is simply sample mean, you squaring it.
Okay.
Similarly, if you had to find method of moment is if you had 3 parameters, then you will go for, after this you will go for expected value of x cube.
Sir, what is M2? How to write M2 as M2
Okay.
square x1 square plus what is it M2? Expansion.
Mute yourself. Yeah. So method of moment, this is the general process.
I'm asking a question, ma'am, actually.
Oh, you're asking question, sorry. Can you repeat?
I'm saying M2 equal to what did you write it, ma'am?
Your voice is not clear.
M2 is written as what, ma'am?
Oh, M2 is written as M1 square minus M1 square plus sigma square.
Okay, ma'am. So the x1 square plus x2 squared. Okay, m1 squared. No, I didn't get how this x1 squared plus x2 squared has to be for m2.
Ma'am, I think it's better if we just write the equation for the various variants once and then come to
No, M2 is second moment. So M2 is second moment. So x1 square plus x2 square plus x3 divided by n.
So what we do is, see, if you have one parameter, if you have
No, what I said is correct. No.
yes, what you said is correct. You have one
Yes,
parameter,
okay.
you find expected value of x, equated this to per sample moment, and you get your value of parameter. Okay, you get your theta hat. You get your theta hat using mm. Now, if you have 2 parameters,
parameter, ma'am, theta, no?
Parameter is theta, it can be anything. First, you find expected value of x. You equate this to m1 to find your first parameter. So let's say theta 1 hat mm. Then you go for expected value of x square and you equate this to m2. Okay. And here you use your theta 1 hat mm to find your theta 2 hat mm. This is what we have done. And what is m1? M1 is your x1 plus x2 xn by n, and m2 is x1 square plus x2 square plus up to xn square by n. Okay. This is the usual process that we follow to find the method of moment estimator. Is it clear?
Yes, ma'am.
Okay. Yes. Now let's move to maximum likelihood estimator.
And hold up a bit, ma'am. So which means that you just add sigma square to get the.
In MME, we will not get any unknown distribution.
You can get unknown distribution.
So even if you get unknown distribution, and you can do the same thing. The first moment will be equal to x1 plus x1 by n. Second moment will be equal to. I mean, if we have to find 2 unknown parameters, we have to take the second moment also. Is it correct?
Yes, yes.
Yeah,
yes.
but
Okay.
I don't mean that. I mean, like in the case of Poisson, we know that the mean lambda.
That's what.
Ma'am, So how do we?
Sorry, ma'am, what you said?
That for unknown parameter.
Let's move forward now. I will, if you can stay back, we'll discuss it more. Okay.
Yes, ma'am.
At the end, because many of you will have live session again at 8, so we will miss.
Okay.
Yeah. Let's look at maximum likelihood estimator. So again, you have some samples x1, x2 up to xn. They are coming from some IIDX. You have a parameter theta, let's say, and you want to estimate this parameter using some estimated theta hat. Now, the way to design this estimator using maximum likelihood, what we do is theta hat ML. To find this theta hat ML, first we find the likelihood function. First we find the likelihood function. Okay, and let's denote this likelihood function by L of x1, x2 up to xn. And this is given as product of fx of xi, where theta is the parameter, I is varying from 1 to n. Let's say this fx of xi is like the distribution has this random variable has the distribution fx. So given any distribution of x, you can just do the product of this distribution, taking all the samples, and you will find your likelihood function. Once you find your likelihood function, you go for log likelihood function. You find the log likelihood function. So L of x1, x2 up to xn is a likelihood function. You just take the log over it. So log of L. Let's write it as L. Okay. You find log of L. Then the third step is you want to maximize your likelihood function. So you want to find such parameter that maximizes your likelihood function. So to find such parameter, to find to do that, you will go for differentiation, right? Like whenever you have to maximize, minimize, we differentiate, we find its value. Now, what we'll do is we differentiate this log likelihood function with respect to the parameter. So let's say if the parameter is theta, we'll differentiate this log likelihood using this parameter theta, and we equate this to 0. Once you equate this to 0, you will get your theta hat ML. So this is the general process steps that we follow for maximum likelihood estimation. Okay.
Ma'am, can you give some or like first step?
Sorry.
Only for take an example and do the first step.
I will do it here. Okay. Let's take. Okay. Let's find for Poisson distribution only. Okay. Let's say x1, x2 up to xn. They are coming from a Poisson distribution with parameter lambda. Now I want to estimate this parameter lambda. Okay. Using the maximum likelihood estimator. This. So first we find the likelihood. Is anyone asking something?
No,
ma'am.
Okay. So first we find the likelihood function. So the likelihood function x1, x2 up to xn. How is it defined? This is defined as product of fx of xi of theta. All right. Now we know that if you have a Poisson distribution, its distribution function fx of x is given by e to the power minus lambda, lambda to the power x by x factorial. Right? Now we have different samples here, x1, x2 up to xn. We'll have to do the product for each one of them. So this is e to the power.
Sorry. So this distribution would be given in the table, right, in the exam, and in case of questions.
Yes. You have got the formula file, right?
No, not ma'am, not for n term.
You did not receive the formula file?
No, not for n term, means not for the final exam.
talking about in the exam, will this be given or we need to memorize this density?
No. It is, I think it is uploaded.
We haven't
Yes,
got
ma'am.
any mail or
Given, ma'am.
That's what I was informed that it is uploaded.
we haven't got any mail or any message.
Not
It's
on
there.
mail,
It's
actually.
that
It is on
file is there.
portal.
This time they were telling that they will be including more lambda.
That file is there. That file is there now.
Can you share that file? Anyone? Because I didn't.
No, the file is not updated. Not for the end term. It is not updated.
It is not updated.
Yeah, that's what I was
Okay,
saying, that
okay,
it's
okay.
not updated for interim.
I had no idea. I will.
It is for quiz 2 only, ma'am.
Ah, that was
Okay,
request
so
too.
the week 12 Reddit solution is not uploaded. Formula file for interim. I will do it today.
Okay.
Ma'am, this time you said you will be including more formula.
Yes, we will be including more formula in interim.
Include these status also.
No, that we cannot.
Solutions. You want the solutions to be included.
Okay.
Sir, I was told to just know the process.
Okay, let's come back to
Okay,
here.
ma'am.
So fx of xi theta is a to the power minus lambda to the power xi, right? Divided by xi factorial. I is varying from 1 to n. Now let's say I have observed few samples as let's say 1, 2, 3, 4, 5. Okay, this is the sample that I have observed. Now what happens? What we can do is you can just do, it will be e to the power minus lambda to the power 1 by 1 factorial, right? Then e to the power minus lambda to the power 2 by 2 factorial, right? Again, it will go on for 3, 4, for 4, for 5. So e to the power minus lambda is constant everywhere.
Yes,
So e to the power minus lambda, it is coming for 5 times. So it becomes e to the power minus 5 lambda, right? And lambda is fixed and you're just summing it over all the xi's, right? Here it is 5. Like lambda to the power 1, lambda to the power 2, lambda to the power 3. So lambda is fixed here. So lambda to the power sum over xi. And in the denominator, you are doing 1 factorial, 2 factorial, 3, 4 factorial, 5 factorial. So after this, we will go for log likelihood, right? We found our likelihood function. Now we want to find the log likelihood.
Yes.
Okay. One thing is you can ignore the constant term also. The
Yes, ma'am.
constant term can be ignored. So you can ignore the constant term that is there here. Okay. So the likelihood function that you got is e to the power minus 5 lambda to the power sum over xi, I varying from 1 to 5. So this 5 is basically because of this sample. Okay. In general, it is n. Now, after this, you want to find the log likelihood. So you find log of L and it will become, so log of e to the power minus 5 lambda to the power sum over xi. Okay. And this can be written as minus of 5 lambda plus sum over xi log of lambda. Correct. This is what you will get. Log of a times b is log of a plus log of b. So you will do log of e to the power minus 5 lambda plus log of lambda sum to the power sum over xi. So log of e to the power minus 5 lambda becomes minus 5 lambda and log of lambda to the power sum over xi becomes sum over xi log of lambda, right? Once we found our log likelihood, yes.
Ma'am, can you please explain from the previous step, like how we got e raised to power minus 5 lambda raised to summation of I equal to 1 till 5 xi.
Okay, so see, here it is I have taken a specific example where you have a sample of size 5, right? 1, 2, 3, 4, 5. This is our sample. Okay. Now what I'm doing is e to the power minus lambda, lambda to the power x1. What is x1? X1 is 1 divided by 1 factorial. Now we have e to the power minus lambda. So x2 is 2. Then we will have e to the power minus lambda, lambda to the power x3 factor, lambda to the power x3. x3 is 3. That's what we have done. So this you will get e to the power minus lambda, e to the power minus lambda 5 times. And this becomes e to the power minus 5 lambda. Right?
Yes, ma'am.
Then you will have lambda to the power 1, lambda to the power 2, lambda to the power 3, and so on. This can be written as lambda to the power 1 plus 2, 3 plus 5. Right? So this is nothing but lambda to the power sum over xi, where I is varying from 1 to 5. Is it okay?
Yes, ma'am.
Ma'am, why we are ignoring a constant term?
Because you're not going to use this constant term later. At the end, you're going to ignore.
Constant term is not dependent on lambda. Constant term doesn't have term lambda.
If you differentiate, it will become 0.
Yeah, it is. So you can generally avoid it. The constant term, you can avoid it. Yourself, please. It's too much noise.
Ma'am, we can also remember this estimator.
If you want, you can. Not necessary. Okay. If you can remember, you remember. Otherwise, you know the process.
Yes, ma'am, because it will reduce a lot of time.
Yes. Okay. Now, once you find your log likelihood function, you differentiate your log likelihood function with respect to your parameter. Okay. The parameter was lambda. I am going to differentiate it using lambda. So this becomes minus of 5 plus sum over xi divided by lambda. Now this you equate to 0 and you get lambda equal sum over xi divided by 5. That is nothing but sample mean. Right?
Ma'am, this value of lambda maximizes the likelihood function. This is correct, no, ma'am?
Yes, this value of lambda maximizes the likelihood function.
Okay, ma'am. Okay.
Okay. So this is how we find maximum likelihood estimator. We saw what is an estimator, how do you design the estimator using maximum likelihood and method of moment. We also saw what is bias of an estimator, what is risk of an estimator, what is variance of an estimator, what is error. This was all in week 8 basically. Now
9.
coming to
What is
week
X bar?
9.
What is the final value of X bar?
X bar is sample mean, no?
I mean, lambda to the power 5 ml.
No, lambda to the lambda hat it is.
It is
Lambda hat.
It is lambda hat ml.
Okay.
So it is lambda hat ml. Okay. Now coming to the Bayesian estimation.
Can just throw a bit up, man. Okay.
Okay.
From here, derivative of okay, it's minus 5 plus summation xi by lambda equals 0. So lambda will be equal to
Sum over xi by 5.
sum over xi. So that is basically lambda cap, right? Or lambda hat.
Yeah, lambda hat.
Yeah.
Okay.
Yes,
Now
thanks.
coming to the Bayesian estimation. Here we are saying that our parameter theta is no longer, this is no longer a constant. Now this is going to be a random variable. We are saying that now the parameter theta is a random variable. So how do we find now if theta is a random variable now, it will have a distribution, it will have its expectation, it will have a variance, everything, all the properties that a random variable have, this theta will also have, right? Because now it is a random variable. So how do you find the distribution of this theta? Okay. So
Like into prior, ma'am.
yes, so what we do here is, like, if you have to find the distribution of this theta, we do posterior is proportional to likelihood times prior. All right. So let's take one example. Let's say the samples x1, x2 up to xn was coming from a Bernoulli P distribution. Okay. Where P is unknown, and it is a random variable. All right. What we are saying is, let's say we have some prior knowledge about this P. We have some prior knowledge of this P. Let's say we are saying that P follows, this P is a random variable. This follows, let's say, a bitter distribution. And we know the bitter distribution will have two parameters. One is alpha and other is beta. Let's write it A and B to avoid confusion. So beta A comma B. So we are saying, let's say we have some prior knowledge of P and it follows a bitter distribution with the parameter A and B. So how do you find its posterior? Okay. So if you have a bitter distribution, how does it look like? It looks like x to the power a minus 1 and 1 minus x to the power
p minus 1.
This is how the distribution of this beta distribution will look like, right? So now this is for no longer the random variable x. Here we are saying we have the prior knowledge of P, and this P now is a random variable. So in place of x, you substitute P. Okay. So it becomes P to the power a minus 1, 1 minus P to the power B minus 1, right?
I'm here prior is for P, unknown P, right?
Yes, the prior is for unknown P.
Okay.
Yeah, where P is a random variable. Now we have the prior, and the likelihood is what? Likelihood is product of fx of xi. I is varying from 1 to 1.
And this could be PMF or PDF, right?
Yes, it can be PMF or PDF, anything.
Okay.
Now the prior is this. Okay. Let's now, if the samples are coming from Bernoulli distribution, okay, you will have some like you will have either P or you will have 1 minus P, right? So let's say out of this n sample, you observed success W times. So we can write it as P to the power W. And we observed failure to be n minus W time. So the product of this likelihood function, so the likelihood function here becomes P to the power W, 1 minus P to the power n minus W. And from here, prior we can write it as P to the power A minus 1, 1 minus P to the power B minus 1. Okay. So what it becomes basically p to the power w plus a minus 1, 1 minus p to the power n minus w plus b minus 1. All right. Now again, this posterior looks like a beta distribution, right? This posterior looks like a beta distribution.
True.
And what are the parameters going to be?
W plus A,
W plus A and then
n
minus
minus
W
W plus B.
Yes, w plus a comma n minus w plus b. Okay. So once you know the posterior distribution, you can find its posterior mean.
Yeah, alpha upon theta.
Yes. So posterior mean is a upon a plus b. So here it will be w plus a divided by w plus a plus n minus w plus b. Okay. So this is a method we find the Bayesian estimate of a parameter.
Ma'am,
Ma'am, for
one
beta
doubt, ma'am.
is beta is alpha. For beta is alpha by beta. So can you scroll the
One
bottom
doubt,
screen is obscure.
Ma'am, how did you assume like likelihood as binomial?
We did not assume. Here it is the problem. It is the samples are coming from Bernoulli P. It is given to us.
Okay, it is given. So we are estimating the Bernoulli P.
We are estimating the Bernoulli P. Yeah.
For that, we assumed a prior distribution for P as beta.
Okay, we are not estimating Bernoulli P. We are estimating this P. Like what is going to be the estimator for this Bayesian estimator for this P.
P. So for that, we assumed like prior P as beta.
Yeah, we
Then
assume that let's say since p is a random variable, it is going to follow some distribution. So let's say we knew from our prior knowledge that this is happening. Let's say this parameter p is following a beta distribution with the parameter a and b. So if a random variable follows a beta distribution, we know this can be written in this form: x to the power a minus 1, 1 minus x to the power b minus 1. This was when your random variable x follows beta ab. But here, in place of x, you have the random variable p, correct? You have the random variable. And if this is following a beta distribution with parameter ab, it is going to be p to the power a minus 1, 1 minus p to the power b minus 1. This is our prior. Now,
those parts are clear.
Sorry?
Those parts are clear.
Okay.
But I'm talking, I have
Ma'am, also I have a doubt.
So x1 to xn,
okay. So x1 to xn are coming from Bernoulli P, right?
Then how this prior knowledge of P and beta, how the transition, I can understand that.
Sorry?
After you have P is coming from P is a Bernoulli P, x1 x2, sorry, I mean x1 x2 xn is Bernoulli P. Prior knowledge of P we have, and then P approximates to beta, how the beta things.
This beta or the final posterior?
The underlined one. No, the right side, just below the prior knowledge, below the prior knowledge of.
We are assuming. It can be anything. Like prior means something that you know beforehand. Like you have some idea. Let's say I knew P is equal to 1 by 2. I can also say that. I can also say that P follows a uniform distribution with in 0, 1. I mean, it depends on your problem, like you get. So I am just taking one example that let's say from my prior knowledge, I know that this is the distribution my P has been following. So I can write this P as a beta distribution with parameter AB. Now, once I know my prior distribution, the likelihood I can always get, because from the samples that we have observed, likelihood we can get from there. And to find the posterior, you will have to multiply your likelihood and prior. And from there, we found that even posterior follows a beta distribution, with the parameter, with your first parameter as W plus A and your second parameter as N minus W plus B. Okay.
Yes, only the first part I had out. So it will be the B approximating theta AB is given.
Yeah, like since the question will be asked in the exam and all, so the prior thing will be given, the prior data will be given to you. The kind of problems you have solved in your assignments, prior data is always given to you, right?
Yes,
The same thing. So here I'm just saying my prior data is that P follows a beta distribution. Okay. Is it clear?
Yes, ma'am. Got it, ma'am. Thank you.
Okay. So once we find the posterior, we can find out, then after this, we can find a Bayesian estimate of the parameter. So we had looked at two different estimate, a Bayesian estimate of the parameter. One was posterior mode and other was posterior mean. We kind of generally use posterior mean to find the Bayesian estimate. Posterior mode we generally don't consider.
What does it mean by posterior mode?
Sorry?
Is it the mean, median mode, that mode?
Yes, that mode only.
Oh, okay.
Yeah. So once you find the posterior, you can find, so once we found the posterior, that is posterior was beta distribution. Now we wanted to find the Bayesian estimate. So I am trying to find the posterior mean. Okay. So the posterior mean, that was, since it was a beta distribution, it is going to be A upon A plus B. So in this case, it is going to be W plus A by W plus A plus N minus W plus B. So this becomes W plus A by A plus B plus N. Okay. This is one example. In the problems, you have a lot of different example, but the method is same.
Ma'am, just a quick clarification, ma'am.
Just
scroll down, ma'am.
Scroll down, okay.
Yeah, like here we are using A plus B plus N, right? In lectures of week 10, I think on couple of places professor has not used alpha. That is typo or what, ma'am?
It has been clarified, right? Before.
Sorry, I have missed that part. That is typographical error, ma'am.
Yes, it is a typo.
Because that has occurred in two places, ma'am. In one place,
yes, we know that.
No, I was not aware. Sorry for that. Thanks for clarification.
Yeah.
Ma'am, can you use gamma distribution instead of Bernoulli P?
Okay.
For the likelihood.
Okay. So let's take the example.
Should we expect these things because gamma distribution has two parameters?
Okay.
So should we expect these things?
Two parameters, no, you should not expect these two things. I mean, two things.
Then we can skip this.
Let's skip this for now. Okay.
Please skip.
Yeah.
Only single parameter will be coming.
Only single parameter.
That means either Poisson or Bernoulli.
No, I mean in likelihood, I'm saying.
Exponential.
Likelihood, for likelihood.
For likelihood. Okay.
Yeah, not for prior.
For
prior, any distribution can come even with the two parameters.
Yeah, that just now we solved for beta, right?
Beta, we assumed something.
Just like prior as a gamma, ma'am.
Okay.
Solve all these things, mean and these things, but
okay.
Just
okay. Let's take one more example from this Bayesian estimation. The process is exact same. I will ask you in between what the result is going to be. Okay. So let's say x1, x2 up to xn, they are coming from a Poisson distribution. Okay, Poisson distribution with the parameter lambda. Now here parameter lambda is a random variable. Okay, let's say from the prior knowledge, we are saying that this lambda follows a gamma distribution. This is from our prior knowledge. All right.
Yes.
Gamma distribution with the parameter A and B. And you have to find the Bayesian estimate of lambda. Let's say we have to find posterior mean of lambda. This is what you have to find. So to find the posterior mean of lambda, first we need to find the posterior distribution of lambda. So to find the posterior distribution, we know this posterior is going to be proportional to likelihood times prior. Okay. Now, how do you write the likelihood function? So what is going to be the likelihood function here?
Multiplication of the distribution.
Multiplication of distribution.
Multiplication of which distribution?
Gamma. Poisson distribution.
Poisson distribution. Poisson distribution. E to the power.
Previously, ma'am.
Sorry.
That we had found previously. You can use that as
e to the power minus lambda, lambda to the power xi upon x factorial.
Yes, ma'am.
I varying from 1 to n. And what is prior?
Gamma distribution.
So what are we going to write the distribution function?
A minus 1 B minus power alpha minus 1.
Sorry, tell me.
Beta.
Lambda power alpha minus 1.
It is a. Let's write it a. Yeah, lambda to the power a minus 1.
A minus 1 e to the power minus beta lambda.
Minus b lambda. Is it clear to everyone? Is this clear to everyone? How did we get prior to be this?
Yes, ma'am.
So
this is gamma distribution, right?
This is gamma distribution.
Lambda.
Yeah.
Okay.
So gamma distribution is written as x to the power alpha minus 1 e to the power minus beta x. We're just substituting x as lambda. That's it. Now we solve this. We'll get e to the power minus n lambda. Okay. Lambda to the power sum over xi. And from prior, we have lambda to the power a minus 1 e to the power minus b lambda. Right? This constant term xi factorial we are ignoring. Now, this whole thing, you can write it as lambda to the power sum over xi plus a minus 1 e to the power minus lambda n plus b. Now, can you tell me what distribution does this follow?
Again, a gamma distribution.
Again, a gamma distribution. And what is the first parameter?
A plus sigma xi.
A plus sigma xi, right? And what is the
N plus b.
N plus b, right? Okay. And we know that if a random variable follows a gamma distribution, its expected value is given by a plus a by b. So here the expected value, the posterior mean.
First term upon second term of gamma.
It is going to be a plus sigma xi divided by
n plus b.
N plus b. So this is the Bayesian estimate for your parameter lambda. Okay. So whatever distribution your sample follows, if the prior is given to you, the method to find the posterior is exactly same. It just your distribution is changing, and accordingly your posterior will change and your Bayesian estimate will change. That's it. But you should be able to identify what distribution your posterior is following. So all this will be available to you, like how does the distribution of beta looks like, how does the distribution of gamma looks like, exponential, Poisson, binomial, everything will be given to you in the sheet. But if you remember it, it's much better.
One question. So how it is?
Ma'am, this formula is not there in the formula sheet.
All
For
this is there. All this is there.
the gamma distribution, it looks different.
No, it is the same.
Same alpha beta are there in place of AB.
Yeah.
Ma'am, for gamma for e power x squared, it's given in some places alpha by b squared, and some places it's given as alpha squared by b squared, beta squared plus alpha by beta squared. Then what is the formula, ma'am, for gamma?
Can you repeat? Can you repeat what we just said?
For variance of gamma, ma'am.
Okay.
Formula, is it alpha by beta square or alpha squared by beta squared plus alpha by beta squared?
It is alpha by beta square.
Okay, ma'am. In some place I saw it is alpha squared by beta squared plus alpha by beta squared.
Alpha square by beta square plus alpha by beta square. No, it is alpha by beta square for gamma distribution.
That is the second moment of gamma function.
Formula sheet has alpha by beta square only. Variance.
Yeah.
Okay, ma'am. Thank you. Thank you.
Ma'am, the posterior mean over here should be A plus sigma xi divided by A plus sigma xi plus N plus B.
Sorry. No. In case of gamma, it is alpha by beta. Expected value is alpha by beta, no?
Yes.
Yes, ma'am. Ma'am,
So it is.
like one thing, like how this is -1, like -1 is not there.
Okay. See, if you have a random variable x that follows a gamma distribution with the parameter a comma b, then we know that its distribution function is given by x to the power a minus 1 e to the power minus bx. Okay. And this we are saying gamma ab. All right. What we got is, let's say for some capital.
When we are telling the distribution function,
Just wait. So if the distribution function here, we got it as lambda to the power sum over xi plus a minus 1 e to the power minus lambda n plus b. Okay. Just compare it. Compare these two.
Okay, ma'am. Okay. Thank you.
Right?
Thank you.
Yeah.
When we are telling the distribution function, are we telling the PDF of it?
We are talking about PDF here.
But in the formula sheet, beta power alpha divided by rho power alpha something is added on that one. What is it there?
Wait, let me see.
He's talking about the gamma part of the PDF.
So for the gamma distribution.
Yes.
Okay, gamma part.
Gamma part.
So that is a constant. So that is why we are ignoring it.
Oh, that's a constant.
That's a constant. Yeah. Like you have not studied gamma function, right? So.
But we are not differentiating it. Then why are we
because it's proportional, so
it's proportional. Yeah.
So we can avoid the constant.
It's a proportional, so we are avoiding the constant.
Yes.
But if you are not avoiding the constant, the posterior mean is multiplied by the constant times. Is that right?
No, it is just proportional.
Okay.
The distribution will look like again something like gamma with the parameter a plus sigma xi comma n plus b. This is how the distribution will look like.
Okay. This is the proportional factor for the posterior movement.
Posterior.
Different.
Yeah. So you find the posterior distribution of lambda, and from once you found the posterior distribution, you can find the posterior mean. Okay.
Got it. Thank you.
Ma'am, practice assignment 10, 13th question. I'm not getting the answer. If you have time, can you?
Problems we can see at the end. Is it
Okay.
all?
Okay.
Let's look at some sorry.
With Bayesian estimation.
Yeah, Bayesian estimation, we can close it now. The process is same.
Okay.
More problem if you want, we can do it in the Thursday session.
Okay. No, I just need a clarification there because I'm not getting the answer. I'm not getting any of the options.
Okay, we'll see at the end. If you stay for some time, we'll see at the end.
Ma'am, you told that you will we will take an example for unknown parameter in MME.
Sorry, we will take example for
Unknown parameter.
Okay, you mean for P?
Mean distribution is
So yeah, if you'll stay back, we'll take that also.
Like we are closing this estimation parts. What I asked.
It's okay. I will take that.
Madam, I have a question. I joined a little late. Perhaps it is already covered. Just wanted to understand what exactly is method of moments, madam, in terms of like, okay, you get a process, but what does the process mean? If you can explain that, it'll be really helpful to me because I seem to be able to solve the problems with that, but I don't understand what I'm doing.
Okay, it will take time. Can we do it later?
Sure. I'll stay back.
Okay.
And are we targeting to complete week 9, 10, 11, and 12 now in this session?
We are going to do hypothesis testing now.
So means you are targeting to complete all these 4 weeks, is it?
Yes, all those 4 weeks.
But only 10 minutes is left. We have sessions from it.
What session do you have now?
Maths 2.
Maths 2. Is it a revision session?
Yes, ma'am. It's the revision and it's important.
Okay, so if you want to go to the maths session, it is fine. You can watch the YouTube session. Right?
Yes, ma'am. Ma'am, just that the last thing, ma'am. It wouldn't take like a long time. Just 2 minutes, ma'am. Can you explain that one thing?
What it is?
Ma'am, like in Poisson, we know that our mean is lambda, or in exponential distribution, we know that our mean is 1 by lambda. Suppose we had given a unknown distribution, how we know what's the mean?
Okay. Wait, I will refer to you one problem here. You go to week 9.
Okay.
Go to week 9. Pain practice assignment.
And should we expect this in term or not?
I will refer to your problem. Wait.
Okay.
Method of moments.
Are you writing, ma'am?
No, I'm just looking at the question. Wait. Yeah, like go to activity 9.5, question number 4. Question number 4, 5.
Okay.
4, 5. There you have such kind of problems.
Okay. Okay, I've done these things. My both the answers are wrong.
You both okay, you check at discourse.
Yeah.
It is
No, I
there.
not referred to the discourse. I previously solved this, but my both answers are wrong.
Okay. So in hypothesis testing, we have seen different tests. So we started with the RZ test, then we went to t-test, then chi-square test, then 2 sample Z test and 2 sample F test. I think it will not work.
In this structure, it is better to add unknown mean and unknown variance.
Sorry, unknown mean and unknown variance.
No, you had just shown a page there. You summarized all different tests. Other page is not visible now.
Oh, not visible. Wait.
No.
Yeah.
No. The other page.
No, we'll talk here.
Yeah,
There,
the page
that
which you-
page is not working.
Okay.
Okay. So in hypothesis test, generally what we are doing is we have some claim and we want to test that hypothesis, whether the claim that has been made or the hypothesis that has been put, whether it is right or not. So whether you should accept your hypothesis or you should not accept your hypothesis. Okay. So first step that we do here is we define what is our null hypothesis. What is our null hypothesis? And the second is what is our alternative hypothesis? So whatever you want to check your claim to be, you put that into your alternative hypothesis. Okay. And you take the null hypothesis as your simple hypothesis. So simple hypothesis is what? Like, let's say, if we are testing for the mean, then we say mu equals mu naught. This is our simple. Anything with equality sign, we say it as simple hypothesis. Then we have alternate hypothesis. We have composite hypothesis that will look something like mu not equal to mu naught, mu greater than mu naught, or mu less than mu naught. Okay. So such anything like this, we call it composite hypothesis. And this is your simple hypothesis. Right? So any problem state, any situation you have, if you have to test for, you have to test some hypothesis. First, you define your null hypothesis. Then you define your alternative hypothesis. Okay, you define your hypothesis. Then accordingly, then after that, after you define your hypothesis, the second step should be, what is a test statistic? test statistic can be a function of your random sample. It can be anything. Then once you decide your test statistic, you decide your test. What is your test going to be? Then on the basis of your significance level, that we also denote it as alpha, and it is probability of making type 1 error. So we have studied two types of error, type 1 error and type 2 error, right? So type 2 error is given by probability of, type 2 error is given by beta. Type 2 error. So when are we making the type 1 error is like when our null hypothesis was true. Okay, when the null hypothesis was true, still we are going and rejecting our null hypothesis, reject H0. So even though the null hypothesis was true, still we are rejecting our H0. So by doing this, we are making an error that we are calling as type 1 error. Okay, and this is given by alpha. Now we have type 2 error. So this error we are making when we are saying that when alternative was true, still we are accepting H0. So when the alternative was true and yet we are not accepting alternative and we are accepting our null, by doing this, we are making another error that we call it as type 2 error. So we want to minimize such error. We want this alpha and beta to be as low as possible. Okay. And there is something called power of the test. Power of the test. And this is given by 1 minus beta. This is given as 1 minus beta. And okay, so we have defined beta to be except H0 when HA was true. So 1 minus beta is going to be reject H0 when HA was true. So alternative was true, then we are rejecting H0. So we want this power to be more and more. Okay. Now, how do we find these alpha, beta power of the test and all? That we'll see. Okay. Before we go there, we have studied different tests. So one first test that we had seen was Z test. Z test for mean. Second was T test for mean. Third was chi-square test for variance. Two sample Z test. And the next one is two sample F test. Okay. Now Z test and T test, they are for whenever we are testing for mean, these are for test for mean. Chi-square test and F test, these are for variance. These are for test for variance. Okay. And in Z test, we also have one sample Z test and two samples Z test. So we have two samples Z test also, and we have one sample Z test. For T test, we have only studied one sample test. Okay. Now, what is the difference between, like, when do we use the Z? Like, let's say we know we have to test for mean, but what test do we use? Do we use the Z test or do we use the T test? How do we know that? So the way to differentiate is like whenever you know the population standard deviation or population variance, in that case, you can go with your Z test. But if the variance is unknown, if the population variance is unknown to you, you go for T test. But like when your sample size becomes very large, Okay, when your sample size is very large, then both the test, like the Z test or the t-test, both will give you the same result. So you can even if you know it is a t-test, you can go with the Z test and you will get the answer. Then the Z value you can use and you will get the same answer. Now,
can you just repeat that once more?
Yeah, like I'm saying, like if your sample size is big enough, okay, let's say it is the sample size is 50 or 100 something, then whatever result your Z test will give, right? Even t test will give you the same value, same result.
Okay, so the variance will,
So
the sample variance will tend to be
in place of the t, like taking the value for t distribution, you can take it for Z distribution and you can solve it and you'll get the answer. You will get the same answer.
Okay.
Yeah.
Thank you, ma'am.
Okay. Now, how do we design such test? So first we will look at set test for mean. First we'll look at test for mean. Okay.
Ma'am, that summary, can you just repeat again, just the last 2 lines?
The last 2 lines, I was saying, like if your sample size is big enough, then in that case, even the Z test will give you the same result.
As
whatever the
t-test.
t-test.
As
Yeah.
t-test.
Whatever the t-test will give. Yeah.
And the previous line is population variance is unknown.
When the population variance, okay. So I will write it here again. Okay.
Right.
We are testing for mean, right? Now we have seen 2 cases here. One was when the population variance is known. Okay. In that case, we use Z test. We go with the Z test. Other was when population variance is unknown. Then we go for t-test. Okay. Now, how do we design such tests for mean? So the first thing is we write our hypothesis. So null hypothesis, we are testing for mean. So let's say we have a population whose expected value is mu and variance of x is sigma square. Okay. So H naught, let's say we want to check if our H naught, if our mu naught equals, sorry, we want to test if our mean is equal to mu naught. Okay. This is a simple hypothesis. Then in the alternative hypothesis, we can have 3 different possibilities. Either we can have mu greater than mu naught, or we can have mu less than mu naught, or we can have mu not equal to mu naught. Okay. So if you draw the normal curve here, let's say this is our mu naught. So I'm saying my null hypothesis is that my mean is equal to mu naught. Alternative is mu is greater than mu naught. So this mu will be somewhere on the right hand side. In the second case, we want mu to be less than mu naught. So it will be on the left hand side. And in the third case, mu not equal to mu naught. So it can be either greater than or less than. Now, whenever mu is greater than mu naught, whenever you have alternative hypothesis to be mu greater than mu naught, it is a right tail test. Okay. Whenever mu is less than mu naught, it is a left tail test. And this is a 2-tail test. Let's look at all the cases here. So first, we look at right tail test. Okay, we have decided our hypothesis. So the null hypothesis is mu equals mu naught. My alternative hypothesis is mu greater than mu naught. Okay. Now we need to decide on our test statistic. So since we are testing for mean, I can define my test statistic to be sample mean. Okay. I have decided my test statistic to be sample mean. And since the alternative hypothesis is mu greater than mu naught, my test is going to be that we reject the null hypothesis whenever your test statistic, this is a T, whenever your test statistic becomes greater than some critical value. So whenever your test statistic becomes greater than some critical value C, you are going to reject your H naught. Okay. Now let's say we have the significance, we want to check for the significance level alpha. We want to check for the significance level alpha, whether we are going to accept a null hypothesis or we are going to reject the null hypothesis. Now, this is the critical value C here. Okay. And this is our rejection reason. And this we are saying is alpha. This is significance level that we have set. Now, this significance level is defined as probability of making type 1 error. And this is happening when, given the null was true, you are rejecting your null hypothesis. Okay. And when are we rejecting the null hypothesis? We are rejecting when the test statistic is going to be greater than C. Okay. And test statistic we are defined as X bar. So this is probability X bar greater than C, given H naught to be true. So what is H naught? H naught is mu equal mu naught. Now we want to solve this. We want to find the value of alpha. So this is going to be, to solve this, we can normalize this, right? I mean, if the sample, let's say the sample, I forgot to mention that, let's say the samples are coming from a normal distribution. Okay. So to convert this X bar to the standard normal form, we will have to subtract the expected value of X bar from X bar, and that will come out to be mu. And the variance will come out to be sigma square by n. So we divide it by sigma square by n, sigma by root n. Basically. Same thing we do on the right hand side. So this becomes C minus mu divided by sigma upon root n. Now this X bar minus mu divided by sigma by root n, right? This is our capital Z. So this becomes probability capital Z greater than C minus mu upon sigma upon root n. And this can be written as 1 minus
FC, yeah, C minus U, yeah.
Yes. So this is our alpha. So significance level came out to be 1 minus FC of C minus mu upon sigma upon root n. Now, if you have to find beta, okay. So what is beta? Beta is probability of making type 2 error. So this is going to be probability that you accept H naught, given that H naught is, HA is true. So you are going to accept H naught, given HA is true. Okay. So HA was defined as mu greater than mu naught, but it is not fixed. It can be anything greater than mu naught. Mu can be anything greater than mu naught. So what we are doing is, let's say we have observed that we are saying that mu is given to be, let's say, some mu1. This is what is given to us, that mu is mu1. So
this mu1 is for alternate, right?
Mu1 is the alternate, yeah.
But if, say, for example, nothing is given, it is only like it is greater than mu naught, then what to take?
Sorry, when?
Say, for example, value of mu1 is not given, it is only mentioned that mu is greater than mu naught, right? Then how to standardize in that case, ma'am?
If it is just given mu greater than mu naught. But find type 2 error, probability of making type 2 error, you need
Okay, so the alternate value will be given.
You need some alternative hypothesis.
Okay, got it. Okay.
That will be given. So we are since we were rejecting H0 when T was less than C. Sorry, when T was greater than C. So we will, yeah. So we will accept H0 when T is less than C, right? And this is mu equal mu1. Now same thing you will do. It's the same process you will follow. So x bar minus mu1 divided by sigma upon root n less than C minus mu1 divided by sigma upon root n. And this becomes FC of C minus mu1 divided by sigma upon root n. Now, if you have to find the power, what will you do? You will just do minus. Yeah.
It has to be strictly greater than or less than, right? Even say, for example, it is equal to the value of C, will accept it or will reject it.
Okay.
Like in case of alpha, ma'am, please come to that alpha.
Okay.
So like we are saying, reject when it is T is greater than C, right?
When T is
greater than C,
when T is greater than C, we are.
So say for example, if my value comes equal to C, exactly equal to C, so in that case we'll accept it, right? It is strictly greater than C, right?
Okay.
It has to be strictly greater than C, right?
If we have defined our test to be reject H0 if my T is greater than C, yeah, then in that case you are going to accept H0 if it comes to be equal.
T won't be greater than C if they're the same, right?
But why I'm asking this question? Why? Because while calculating P value, hope we will come to P value also, ma'am, right? Then I will ask that question. Then I will ask that question. Okay.
Madam,
No
should we, for alpha, instead of mu, should we have mu0 written over here? Because mu equal to mu0 is.
Sorry, can you repeat? In place of alpha?
In the value of alpha, should it be mu0 rather than mu? Or is it the same because mu equal to mu0?
Oh, okay, sorry. It is mu0. It is mu0 because
okay.
We had assumed H0 to be true.
Yes, okay.
Mu is the population variance and mu0 is the hypothetical variance, is that right?
Mu0 is what, yeah. Mu0 is what we are saying that our mean is.
Mu0 is the hypothetical variable, is that right?
Yes.
Precise values.
And x bar is the sample variance.
Yes.
Sample mean, not sample.
Sample mean, yeah.
Sample mean. Both are mean, okay. And sigma is the population variance, and we are comparing the difference between the sample to mu0. That is a hypothesis with mu mean. Okay.
This is a very basic.
Yeah.
Yes, ma'am. We can proceed. Yes, ma'am.
Yeah.
So this is for right tail test. Now, same thing you will do if you have mu greater than mu0. For left tail test, it is.
And we were talking about power, ma'am. 1 minus beta you were talking.
What is the power, ma'am? We are just, I'm not able to physically connect that one because alpha and beta is type 1, type 2 error.
Yeah, so
and 1 minus beta is the power.
So power is what? Power is like, even though you you knew that alternative hypothesis is true, like let's say alternative hypothesis was true, and you are accepting your alternative hypothesis. I have defined it here, no?
I already told that one you got to keep both alpha and beta as small as possible.
Yeah, so power of a test is, given HA is true, we are rejecting H0. Okay, this is what this probability we fine for power. So we want our power to be as more as maximum as possible. Because it says HA true, you are rejecting H naught. Okay.
That means you expect that to be as high as 1, that's it.
You expect it to be as high as
Power.
possible. Yeah, power.
Then the question may be while calculating beta, right? And we know that beta should be as low as possible. Then what is the necessity to calculate power? Because if my beta is going low and low, then my power will definitely will go high and high.
That is the point I was also.
Yes. So if you can reduce your beta, your power is going to be high.
Yes, then what is the necessity to calculate, introducing one more term? There must be some logic behind that. That's what I know. It is not related to enter exam. But quickly something can be shared, that's fine. Otherwise, we can move ahead, man.
Okay.
That is error 1 and error 2, sir. You closely follow that error 1 and error 2. Then we can understand beta. Anyways, we are calculating beta. Then to minimize that beta, automatically we'll be getting more and more chances of getting we ourselves the hypothesis correct kind of thing. That is the ultimate purpose, right?
Correct.
Sounds a redundant factor we are shifting. But there is more questions on the level of significance and power, no?
There are more questions on significance, level, and power.
Power is. All right. So for exam purpose, these two are important.
Ma'am?
Yes.
In case of right tail, left tail, and two tail test, it's not possible to find the numerical value of beta, right?
Why not?
Because in that case, your alternative hypothesis, that is mu is in some range, na? It's either less than or greater than or not equal to. So you don't know the exact value of mu1. So your expression for beta would be in terms of mu1.
So this alternative hypothesis, right? This will be given to you. Right? Let's say instead of saying that mu greater than mu naught, it will be given that take alternative hypothesis to be, if the alternative hypothesis is mu equal mu1, then solve for beta. Then if you know, once you know this, you can find your type 2 error.
Okay, fine. So we will be given, na? Otherwise it's not possible.
It will be given. It will be given.
Okay, thank you.
Yeah.
Madam, when do we actually say that this is a proportion-based thing or a mean-based event? Basically,
proportion-based thing, okay.
Because there was one question in which it was given 36 out of 100. I went by saying it's proportion, but turns out it is not.
But you must have gotten the same result. Did you not?
Result is same, but when I pick the options, multiple options are there, right? You pick the option saying it is a mean based or a proportion based, that went for a toss.
Okay. So let's say there is something like there is some population, let's say you have taken a sample from those population, and out of, let's say the sample size is 100, and we are testing for something, and we are saying from this sample, we got our P to be, let's say 0.60.
Okay. So if somebody says that is 60 out of 100, then we go by mean. Is that the way it is?
Both things you can go through. It's not an issue.
No. What I mean to say is in the multiple options, when I have to actually pick, which one do I pick? Should I go for the mean one or should I go for the proportion in this particular case?
Which question? Do you have any specific question in mind?
I understand.
It is in graded assignment week 11.
Correct.
assignment week 11.
Yeah, because of that confusion, all three options are also getting wrong.
Wait.
I think it is question number 3 or 4. No, just
Okay.
Yes,
So,
you're right.
okay, so it is question number 3.
Yes.
There it says, I will share this. Suppose X is normal in mean mu with mean mu Bayes 9. You are taking 100 IID samples of X and the observed sample mean is 11.8. Okay, sample mean is given to you that we have observed is 11.8. Now you have to test like what conclusion would a Z test reach if the null hypothesis assumes mu equal 10.5 against some alternative. So
Sorry, this one I went for right. This one went for right. Sample mean is what I went for. That was that X bar is what I went for.
There's no.
Oh, can you go to question number 6, please? Can you go to question number 6?
That is 0.36, something like that.
All right. A manufacturer supplies fuses approximately 90% of which function properly. A new process is initiated whose purpose is to increase the proportion of. Okay. So we want to test whether P is less greater than 0.9. Okay. So P equal 0.9 and P greater than 0.9. Okay. We obtain a random sample of 100 such fuses manufactured with new process and found that 8 out of them are not functioning properly. Okay. Portion of properly functioning fuses is about not binomial. Okay. So what is the correct answer given? Yeah.
It says it's sample mean, but I went for proportion looking at the 90%.
I also went for that.
Okay, so when you were saying for the options, you were not saying for question number 3 before.
No, question number 3 was just fine because it was saying 11.8 and it was pretty clear it was sample.
No, I because I remember when we were doing week 11, it had come and that time it was question number 3 and option 1 seemed right. So we didn't correct it that time. Whatever it was, we went through it. But yeah, in that case, if you're saying yes, you can use any of it.
No, I can't pick any of them. No, there is only 2 options I had. One of the 2 I had to pick. It's proportional sample.
Yeah.
No, I got it wrong. The entire thing went for a toss because I picked proportion. The others are right.
But yeah, I got it.
But
Right tail and significance and all those things, right? But this one, because I picked proportionate, went for a toss.
Ravi, there's a good news that in previous session also we discussed this thing with Mayur sir. So he said this kind of question will not be there in end term. They have taken care because both the options are given, proportion and mean both are given, right?
I don't want to take my chances. That's the reason
Yeah,
I'm
both
asking.
of them should be correct. I mean, it depends on what test statistic we're trying to use. It's just,
both of them should be correct, ma'am, right?
It's like the yeah, it's like the test statistic is just the function of your random sample.
On a lighter note, I said that he has.
Okay, yeah, fine.
We can move ahead with this.
Yeah. Okay.
Madam, can we go to the part that I was just asking a little earlier on method of moments, or do you want to do it a little later?
In the previous question,
chi-square is pending. Chi-square F test.
Okay.
Yeah, a lot of tests is pending. Okay. So we saw only one tail test, right? Now, if we have a 2-tail test kind of, so there one mistake that many of like doubt that comes is like, okay, I will just directly go from alpha. So let's say I'm taking my test statistic to be 2 and the test is going to be reject H naught when mod of X bar, I will write it here. So test statistic is X bar and my test is, this is for 2 test, reject H naught if mod of X bar is greater than C. You can take this or you can also take this mod of X bar minus mu greater than C. You can use any test, you will get the same result. I think I had shown this in the session before. So if you find alpha, you will do probability that you reject H naught. So if I go through X bar greater than C, given my mu equal mu naught, then what we do is we'll have to subtract mean from both the sides. So it becomes probability mod of X bar minus mu naught greater than C minus mu naught divided by standard deviation sigma upon root n, right? So here also sigma upon root n. And this term is, we know it is Z. Probability mod of Z greater than some C minus mu naught divided by sigma upon root n. Now, this probability can be written as 2 times probability Z less than minus of this term, So it becomes mu naught minus C divided by sigma upon root n. Okay. And this is your alpha. Now from there, let's say we know our significance level alpha. From there, you can find C. Okay. Now, if you have taken your test to be reject H naught if X bar is greater than C, then whatever C you have found from here, you will, and whatever X bar you have observed, you compare these two. You compare whether mod of X bar is coming out to be greater than C or not. If it doesn't come out to be greater than C, then you accept H naught. Otherwise, you reject H naught. Okay. But if you take this as your test, I mean X bar minus mu greater than C, then you don't have to subtract mean again. You don't have to subtract mu again from C. So if I take X bar minus mu greater than C, given mu equal mu naught, you don't have to take subtract mu naught from C again here, because we have already subtracted it from one side, and we have already brought our sample mean to equal to 0, mean to be 0. So we don't have to do it again. We just divide it by standard deviation and the process stays the same.
Answer will be same,
Final answer will be same. Then whatever C you will get, you will compare using this. So it's not like you start from one test and you, when it comes to actually deciding factor, you take some other test. It should not be like that. Just be careful. So both will give you the same answer, but you should stick to one.
Can you explain the 2p of Z less than mu naught minus C or C minus mu naught, ma'am? That is the confusion.
Mu naught minus C. Okay. See, I've explained many times before also in the session. See, whenever you say probability mod of Z greater than some C, okay?
Concept is okay, ma'am, but thing is the inequality, how to handle that. That is the only.
Yeah, see, capital of Z greater than C. Okay, let's just see some value, some constant. Now, this term inside the bracket, you can write this as Z greater than C and Z less than minus C, right? So this becomes probability that your Z is greater than C plus probability that this Z is less than minus C. Okay. Now, if this is a standard normal distribution, the mean is going to be centered at 0. And this is going to be your C, this is going to be minus C. So you have to find the probability that Z is greater than C and Z is less than minus C. Okay. So basically you have to find the value of these two shaded area. What is the probability of this? So you know that the normal curve is symmetric around the mean, right? So this value is going to be the same as this value. Both are same. So if I can just find FC of minus C and do it 2 times, we will get the overall area. That's all we have done. So it is 2 times probability Z less than minus of this. Okay. All right. So this was all about Z test. Then we have t-test, when the sample is, when the population variance is not known to us. So when the population variance is not known to us, we go for the sample variance and the process still remains the same. So what we say is, we have, in case of t-test, no, you're not, Manan, you're not audible. In case of t-test, which is also test for mean, this is also test for mean, and in this case, your sigma square is unknown. Let's say the samples x1, x2, up to xn, let's say the samples are coming from the normal distribution. These are all IID, normal distribution with mean mu and variance sigma square, where sigma square is unknown. Then we have, let's define our H naught to be mu equal mu naught, HA to be mu greater than mu naught. Okay. We define our test statistic to be same P equal X bar. And the test is, we reject H naught. We reject H naught if X bar is greater than C. So since here the sigma square is unknown, so what we do is, instead of sigma square, we replace it by S square. We just find S square. Once we replace it by S square, then given your null hypothesis, your T minus mu naught divided by S upon root n, it becomes T distribution with n minus 1 degrees of freedom. Okay. And the whole process remains the same. Then this T value will be given to you and you will just have to substitute and get your alpha. Any doubt in using finding, any doubt in t-test?
No, ma'am.
Okay. Manan, you have raised your hand. Any doubt? I'm not able to hear you. Okay, then you put it on chat box then.
Ma'am, how it is different than the Z test, ma'am?
How is it different than Z test? So what I told is, like, when the population variance is unknown to us, we go for t-test. Rest everything is same.
Okay, okay.
Then we'll have a T distribution.
Ma'am, so what does this particular S actually, so what does it represent actually? We don't know the population mean, right?
Yeah.
Variance.
S
Yeah,
is
population variance. Yeah, if we don't know the variance, right?
S is sample standard deviation.
Okay. Okay. Okay, so you mean to say we have a sample, okay? From that sample, we estimate, we try to calculate the population.
We try to calculate the sample variance, and we
Sample
will
variance.
use that sample variance to get the T distribution.
Okay, understood, ma'am.
And yes, Manan, even in t-test, we are taking our X bar test statistic to be sample mean X bar.
Madam, sorry, but on the beta that you gave an explanation, I still am having some doubt. Beta is accept H naught when alternate is true, right?
Beta is when the alternate is true, you
We
are
accept the
accepting
H naught.
Yes, right.
Yeah. So how do we represent that when it comes to the equation? Because reject H naught is very clear. I go for the alternate hypothesis and go with it.
Yes. So you just, okay, let's say The alternative hypothesis was mu
True,
greater
but I
than mu naught.
accept. Yeah.
Then you reject H naught when your T is greater than C. Okay. But here in beta, you have to do probability of accepting, right? We are rejecting when this T is greater than C.
Correct.
So when will you accept? When this T is
T less than C.
Right?
Okay. So I go for the same.
Same test statistics. You just have to change the reason. So when you are rejecting for T greater than C, you will accept for T less than equal to C.
Okay, so whatever be the condition that is there, let's say mu1 is greater than mu2 or whatever be it, I reverse the sign and then I just go with it.
Yes.
And how does it work when it is not equal to? We'll say equal to?
When it is not equal to.
Yeah.
Okay, so there also, oh, we didn't see it, right?
No.
Now we change the sign again. We have modulus there.
Change the sign again.
Change
Okay. Yeah. So, okay, right. Oh, okay, well, let's do it here. So when you have alternative to be mu not equal to mu naught, you define your test statistic to be X bar, right?
Yeah.
Now test is reject H naught if mod of X bar is greater than C.
Correct.
Then when will you accept H naught? When mod
It
of
is
X
less than
bar
C.
is
Less than C. So I go with mod of X bar less than C and then
yes.
compute it. Okay.
Yes.
Okay. All right.
Are you going to beat our P value also?
It's a little tricky for that. I normally go for computing the power and from there I get back to beta. But that's
okay.
That's not necessarily the best way. So thank you.
All right. Now, yeah, let's come back to P value. In two samples test, we compare the mean average of two sample given to us. Yes, that is what exactly we do in two samples test, Manan. Okay. So P value, what we do is to find the P value, we find probability. So let's say the test was right tail and the test statistic was given to be some just statistic we took as X bar. Then to find the P value, we do probability mod of probability X bar greater than what X bar you had observed. What X bar you had observed. Okay. So let's say okay, what should I write? Let's write it as C observed.
Ma'am, what's my H naught and HA here?
H naught is mu equal mu naught and HA is mu greater than mu naught.
Thank you.
Yeah. Okay. And the test statistic is X bar. So basically, in when you're finding the P value, so P value is nothing but the lowest significance level at which you are going to reject the null hypothesis. So if the test is right tailed, let's say this is our mu naught. Let's say this is our critical value for which we have the significance level alpha. All right. Now, if the P value comes out to be in the okay, let's forget this.
Ma'am.
So
I think while calculating P value,
we don't
when my X bar becomes exactly equal to C, in that case, whatever my alpha comes out, that becomes my P value, right?
When X bar comes out to exactly C, then Yes, then it will be p-value.
That alpha becomes my p-value, right?
Yes, yes.
But normally when we test, so the x bar has to be strictly greater than c to reject my null hypothesis, right? This is the only doubt which I am asking. So in case of normal testing, say for example, I am testing right tail test. So whenever my x bar is strictly greater than c, then only I will reject my null hypothesis, right? That is my first question, correct?
Yeah, if it is strictly greater, then you reject your.
And if it is equal to c, then we don't reject, right?
If it is equal to c, by definition, you should not reject it.
Because as per definition, it has to be greater than, right? But while calculating p-value, the value of alpha which we get by equating x bar to c. So that alpha is my p-value, right?
Yeah, basically p-value is
that lowest significance
probability.
level, the lowest significance level.
Probability, yeah.
Yeah, so the lowest significance level. So when x bar is becoming equal to c, so the whatever value of alpha I am getting, that is becoming my
p-value.
Okay, thank
P-value.
you.
Yeah.
Thank you.
So whenever you have to find the p-value, you just replace your now in place of we don't need critical value. So whatever you have observed, from there you can find your p-value.
So on both sides we write x bar minus mu, x bar minus mu, something like that. Yes.
Yeah, like if h naught is true, then both sides you will have to do probability mod of x bar minus mu naught. Whatever you have observed, let's say. So Manan is saying we are right. We have written it as t. So I will just write it t here. Let's write it t here. So t minus mu naught, same thing. The way we had proceeded before. Once you solve it, you are going to get your p-value.
Okay, thank you.
Okay. In chi-square test, we are doing the test for variance, right? We are testing for variance. So let's say.
Excuse me, ma'am.
Yes.
From the p-value, can we decide accept h naught or reject h naught?
Yes, we can decide. So
how we can decide?
Let's say this is my test. H naught equal mu naught, HA equal mu greater than mu naught. Okay. This is our test. We got, let's say, the p-value to be, for example, let's say we got the p-value to be 0.02. Okay. Now we want to test whether at significance level to be 0.05, can we accept or reject the null hypothesis? Okay. We want to check whether at this significance level, can we accept or reject the null hypothesis? So let's say this alpha here is 0.05. Now, this is our significance level that we have fixed. Now, the p-value that we got is 0.02. So, this 0.02, is it going to be inside this rejection region or outside this rejection region?
Inside the rejection region. It is less than 0.05.
Inside this rejection region,
Yes,
right? So, you got your p-value to be 0.02. Then we will say we are rejecting our h naught. So at the significance level 0.05, you can reject your h naught.
Thank you, ma'am.
Yeah, similarly, you can check for one side, like left tail or right tail. It is not inside the acceptance, it is inside the rejection region.
Ma'am, can you please repeat this part?
Yeah, so let's look at this figure. Okay, so I'll just change the color. So this shaded region in red, right? We are saying this is alpha. This is our significance level that we have fixed. And let's say we have fixed this alpha to be 0.05. Now at this significance level, we want to check whether we are going to accept the null hypothesis or we are going to reject the null hypothesis. Okay. So we got our p-value to be 0.02. Okay. We got our p-value to be 0.02. Now, this p-value, is it going to lie inside this rejection region or outside this rejection region? This is going to lie inside this rejection region, right? So any z that you had observed, this is going to be inside this rejection region. And for that, you have this p-value 0.02. So since this is inside the rejection region, we are saying that at significance level 0.05, we are rejecting our null hypothesis.
If it is the p-value is 0.06, ma'am, what will happen?
If p-value is 0.06, then that is coming out to be outside this.
It is both inside and outside, no?
Yeah, it can go inside or outside.
Yeah.
I mean,
so what do we do that one then? Partially we accept it, partially we reject.
Of course, significance level is 0.01, and we will accept null. Is it right? Okay.
So anything less than 0.05, we will reject it. But if anything is exceeding 0.05, then it is spreading between acceptance region and rejection region. So how do we conclude it?
Okay, so in that case, you know the usual process, right? I mean, you know the usual process, like if you have the significance level, how do you reject or you go through the critical value and you get your from there you test for whether you are accepting null or you're rejecting null.
Okay. No, I'm not able to connect.
See, I'm saying that if this alpha, I mean, you're saying if p-value comes out to be 0.06.
Yeah.
So this is outside this. I mean, some part it's outside the rejection, some part it's inside the rejection.
Yeah.
So
that's right. That's the part.
you find, okay, then you know how to, you know how your general method, usual method. You find the critical value, you test for whether your x bar, I mean, your test statistic is greater than C or not. If it is greater than C, we say we are rejecting this null at 0.05.
Yeah, but C is a point, is it?
Critical value. C is critical value.
Critical value is a point, is it? Not
It's
an
a
area,
point.
not like alpha. Yeah.
No, alpha is an area. Like
Alpha is an area and C is the point on the
C is the
x-axis.
point. C is this point.
Yeah.
After this area is alpha.
Yep.
P value is also an area.
Yes, the both are
Probability, right?
areas.
Probability.
Yeah.
Alpha is probability. P value is probability.
Yes. So that's the reason why I asked now if the p value is spreading between acceptable region and rejection region. How do we make a conclusion? So what you're telling it is just treat a C value, take a C value.
You find a critical value and then conclude.
So critical value is the p-value, madam. Whatever we find as critical value.
No. Critical value is not, p value is probability. It cannot be C. So p value is also significance level, basically.
Correct. Okay, ma'am. Now, how do we find the C value corresponding to the P value what we are referring to? Should we go to Z table and find out?
Both of them are probabilities. How will you go into the table?
Sorry. Can you repeat?
If for both the things, if they're coming from the same table, how will it help? It will not help.
I did what both things?
No, the question is
C value. He was asking if P value and C value both come from this Z table. So, okay, sorry, go on, please. You continue. Sorry, I said something.
Okay, I can ask the question, ma'am. You were telling that at the time when the P value is 0.06, then you take reference to C value and make your conclusion. Is that right? That's what you said.
Yeah, from there you can conclude.
Yeah, how do we get the C value there?
You know your alpha, right?
Yeah, but I know the alpha, but I don't know the C value corresponding to the P value I calculated. So I'm going to compare.
No. C is for critical value, is for
Given.
finding the alpha.
That's given. That's given. Is it?
No, C is not given. Your alpha is given to you.
Okay. Alpha is given, right? Okay.
Alpha is given, right? Alpha is 0.
Yeah, you're right.
Alpha is given. So if alpha is given, how do you find
1 minus
critical
alpha
value?
is 1
No.
minus alpha is the C
If
value,
alpha is given, you know what is the definition of alpha?
the type 1 error. That is the.
Yeah. From there you find your C. Right? From there you find your C.
Okay.
And whatever test you have defined, from there you check whether your T is greater than C, T is less than C and all.
Okay, T is a point in, is a point here now. Okay. Okay.
Sorry, what is the point?
So we are taking reference to the points now. T is also a point and C is also a point.
Oh, T is the test. P value is not a point.
T value is
okay, I will refer to you which session.
P value is a point and P value is not a point.
So wait. So you can refer to this extra session.
Okay.
2 that was taken. Extra session 2 that was taken for week 11.
Week 11?
Yeah, week 11.
Okay.
Okay, P value, like one whole session is for P value.
Okay, ma'am, I'll take it. Thank you.
Yeah. Already it's 8:53. We have 3 more things to complete.
Right.
Yeah. So if you have doubt in P value, you can go and watch the session. Okay. Okay. So in chi-square test, we are testing for variance. Okay. Now let's say the samples x1, x2 up to xn, they are IID with normal mean and variance sigma square. We want to test for variance. So H naught is sigma equals sigma naught and HA is sigma greater than sigma naught. This is a right tail test. Our test statistic, we take it as S square. S square is defined as 1 upon n minus 1 sum over xi minus x bar whole square, I varying from 1 to n. Now the test is we reject H naught. We reject H naught if S square is greater than C square. Okay. Okay. Now this is our test. Given H naught, given this H naught to be true, what we are saying is this n minus 1 S square divided by sigma square follows the chi-square distribution with n minus 1 degrees of freedom. Okay. So to find the significance level in this case, you will do alpha equal probability that you reject H naught. So probability that S square is greater than C square, given this mu naught is true. Okay. So given this mu naught is true, H naught is true. That is sigma equal sigma naught. And this can be given as n minus 1. Now we want to convert this S square to n minus 1 S square by sigma square, right? So it becomes n minus 1 S square divided by sigma naught square greater than sigma square S square, sigma square n minus 1 sigma naught square. Okay. And this is, we know it is a chi-square distribution with n minus 1 degrees of freedom. This you can write as 1 minus probability chi square with n minus 1 degrees of freedom less than equal to this. And this can be written as 1 minus f of chi square n minus 1 square of c square n minus 1 divided by chi naught square. Right? And this value will be provided to you. So you can easily find your critical value. Okay. The process is same after this.
I think process is same for less than also, right? Like this is the right tail.
Same for
left tail also.
Same for left tail also, right?
Now, what about two tail test in case of chi square? Like when we will say that sigma is not equal to sigma naught.
One question was there in the practice assignment. So there what we had done, okay. So in case you get your HA,
sigma is not equal to sigma naught.
Yeah, sigma not equal to sigma naught.
And then how to proceed with that? We have to take that bar modulus again.
Yeah, so if your alpha is 0.05, say, then alpha by 2 you find so alpha by 2 is going to be what? Probability that you reject H naught. Okay, this will become complicated. So okay. Okay. Mhm. Let it come. Mhm. Yeah. So okay, now if H naught is sigma equals sigma naught, okay, and H is sigma not equal to sigma naught. Test statistic is S square, and the test is okay. The test statistic is S square, and we know n minus 1 S square by sigma square will follow the chi-square distribution with n minus 1 degrees of freedom. Okay. Okay. So given H naught to be 2, you find out what is this going to be. Okay. So let's say if I have a sample of size 100, so n minus 1 will be 99. S square you will have from your sample, you can find it from there, and sigma square is going to be sigma naught square. You find this value, okay, you will get a particular value. Now since it's a two-tailed test, you will have to make it alpha by 2 and alpha by 2. So this, what we will do is chi-square looks something like something of this sort. Okay. Okay, so what you will do is you will find your chi-square distribution. So f of chi-square of n minus 1 of alpha by 2. So f inverse of alpha by 2 you will find for both the side. Okay. Yeah, it is a little different, but actually the same the way we are going to do this, you can do the same thing for all the tests. I mean, even if you are doing the Z test, no, so you can get like in Z test, like
Remember that modulus root will not work here. Modulus root.
Modulus.
The way we do for G test.
It will see it is not centered at mean or something, or centered at some value.
Yes.
So there you have to take two different equalities and then find it separately.
Ma'am, so how do we solve here? We get a value for n minus 1 s square by sigma square, and then what do we do?
Wait. See, this is chi-square test for variance. Okay.
Yes, ma'am.
Now, if it is right tail test, we did s square greater than c square. If it is a left tail test, we'll do s square less than s square.
Yes, ma'am. Yes.
Now, if you have two tail tests, you are going to do s square greater than c square, where alpha by 2 equal probability s square greater than c square.
Okay.
Or you can do s square less than c square, where alpha by 2
So
is.
we'll have to calculate both, ma'am, right?
You can calculate anyone. Or the same as you had calculated f test.
F part EGG, because in F part we get a sense, right? We get a sense that whether it is greater than 1 or less than 1. But in case of chi-square, we don't get a sense. No?
In chi-square,
in case of F, what happened, ma'am? When we divide one sample by other sample, we get a hint that whether it is greater than or left hand. Okay, got it, ma'am.
But there also you can use any one of it. You don't.
Yeah. In that case, any one of it is clear. But here also you are saying that any one of it will give the answer, right?
Oh, any one of it should give the answer.
Ma'am, which docket is this, ma'am? This is not uploaded in dashboard.
Yeah, it is. You can find it in the formula file.
No, this is uploaded.
Okay. It is in week 12 or what? Week 12.
It is week 12. Week 12.
Okay. Ma'am, if time permits, can we solve a problem on two-tail chi-square test, ma'am?
So it's
two-tail chi-square test.
It's a OR case. S square is greater than c square, S square is less than c square. It's or it's given as a either one of it we can use it then.
Yes, either one of can be used.
But I don't know that on
We
which
cannot
side,
multiply it by
on which side my value will lie. That is coming on the right hand side or is coming on the left hand side. No, I don't know. If it is within the acceptance region, then that's fine. I will accept it.
Okay, for now, just leave this two-tail part. Okay, we'll discuss it. If there is two-tail, we'll discuss.
Yes, because this was not responded on dashboard also. Sorry, discourse.
We'll discuss the two-tail test.
Okay, ma'am. Okay.
Just leave it.
For exam, it's not required. I think. Is that, ma'am?
Yeah, even problems we did not solve for two-tail test. I guess.
We can't say chi-square is important.
Ma'am?
We'll look at two-tailed chi-square test. You have many chi-square tests in additional content actually. I mean, those are not for exam, but all are for chi-square.
Those are goodness of fit, and also those are
yes.
Those are yes, those are clear. They are not important from exam point of view, but I think chi-square is important from exam point of view. That's why.
Ma'am, for F test, we have to calculate significance level by 2.
Yes, you do alpha by 2.
In graded question, there was a question, it was equated to sigma, ma'am, FZ value.
Was it a two-tailed test?
Yes, ma'am.
May I answer?
Maybe is it by mistake?
Then may I answer? I had asked this question on Discord, so I had got the answer also.
Okay.
So if it's a two-tailed test, then only we have to take alpha by 2. And if it's one-tailed test, then we have to take alpha. So ma'am, whatever question you are referring in graded assignment, that is a single-tailed test. Because it is being asked that whether the sample B is greater than sample A. So when this kind of statement is written, it means it is a one-tailed test. And in that case, we have to use alpha, not alpha by 2. When it is not equal to, then only we have to take alpha by 2.
Yes, only for the two-tailed test, you take alpha by 2.
Otherwise, alpha. Otherwise, alpha, we have to take alpha. That is the reason why alpha value is given.
Okay. Okay.
Okay, so 2 sample set test, we test for mu1 equal mu2. That is what we want to check, right? So alternative is going to be mu1 greater than mu2, or mu1 less than mu2, or mu1 not equal to mu2. And in case of two-tailed Z test, we take the test statistic to be x power minus 5 bar. And given the null is true, the distribution is normal with mean 0, variance sigma 1 square by n1 plus sigma 2 square by n2. Okay. And from here, you find your alpha value. The process is again the same, the way we had done for Z test. We know the distribution of x power minus 5 bar. We subtract its mean, we divide its standard deviation, then we find the C value and decide on whether they are going to accept or we are going to reject. So if it was a right tail test, I mean, the inequality is mu1 greater than mu2, our rejection reason what? X bar minus 5 bar greater than C. If it was mu1 less than mu2, rejection reason was y bar minus x bar greater than C. Otherwise, it was x bar minus y bar greater than C. Yes.
Hello.
You're audible. Can you?
Yeah, ma'am. Ma'am, I was saying that in this two-tailed test for two sample, for this chi-square test, you said there are not enough problems in our practice or graded assignment. So, ma'am, how important is the two-tailed test for chi-square test? I mean, two-tailed for chi-square test. How much it is important for n term? Hello.
Yeah. So two-tailed test. You can skip for now. Two-tailed test for chi-square. Okay.
Because we have to calculate alpha by 2 for it will give the value for any of the.
We'll discuss this two-tailed test, but leave it for now. We'll discuss it in Thursday session. Okay.
Okay.
Thursday, or if needed, we'll take one more session.
Yes.
Ma'am, after the mock test, do we have a discussion?
Sorry?
After the mock exam is over, mock quiz or anything, do we have a discussion?
After the mock session is done, no, we do not have discussion.
Yes, ma'am. Thursday session is for mock discussion only.
Mock discussion only. Yeah.
Yes, yes. Thursday session only for mock.
It's already scheduled, huh?
Yes, yes. And Friday revision 2 is there. Friday revision 2 is there.
No, there is no
No,
revision.
there is no other revision session.
Friday there is a session, man. Just check calendar.
No, there is no revision session. I just checked.
Friday, Thursday is the mock revision, and
Last session is on
Friday
Thursday.
there is a
Friday. There's nothing there.
Yeah, Friday there is no session.
There was something initially actually in the calendar, but
Initially it was there, but
ma'am,
now
then it has
it's
been
removed.
removed just in the evening because it was there till afternoon. Till afternoon it was there, ma'am.
Yes, ma'am.
And,
Yes, ma'am.
and even Srikant sir, Srikant sir had said that he will come on Friday. In last session, he came on Thursday and he
We
had
want that one, ma'am.
and he confirmed that on
If
4th.
needed, we will put the session. Okay.
No, not needed, ma'am. It was pre-planned. He said that I think he will be completing week 8 to week 12, and he will complete from week 1 to week 7. And this session was there till afternoon. And this session was there till afternoon.
I think it's better to start early, ma'am, around because already maths is there.
Yeah, it was from 8 o'clock. It was from 8 o'clock in the evening.
Oh, 8
Okay.
o'clock.
If Thursday session is not enough, we'll schedule of the Friday session again. Okay? We'll put it in the calendar of the Thursday itself.
Who will take Thursday session?
Sorry.
Who will be taking Thursday session?
So almost everyone will be taking the session on Thursday.
Everybody will be there in different breakout rooms.
Yeah, so everyone will be almost taking the session. So
okay.
Ma'am, only just please confirm that one all these things are getting recorded because we rely upon that one heavily to spend the whole Saturday on that.
On which?
On Thursday's discussions, because the breakout room discussions we don't want to miss it. Yeah, because we will not be in a position to attend to all. So one of the things, probably most of the guys will be there in the main session.
Ma'am, is there any special link for breakout session?
Because I think that is the one which really they spend more time on specific doubts. I believe breakout session is to address specific clarifications. So means.
But there is only a one Zoom link.
No, 3 breakout sessions are there.
Where it is? I can't find it.
We got an email today. It's a concurrent running of 3 breakout sessions along with the main discussion.
And did you join a little bit late today or what?
No, whatever it is, whether it is right time or late time, but still.
No, ma'am clarified at the beginning that there will be a main link, and in that main link itself they have facilitated it that there will be 3 different rooms. So I think they will provide different links at that during that session itself.
Because till now there is only a
no. This question was getting discussed in a couple of times, and I think someone named admin has also floated a message in chat box also.
Madam, sorry to interrupt the entire thing, but if it is okay with you, can we go to the method of moments that I was asking earlier?
Yes.
Yeah. Can you just
Hello, ma'am.
Yes, ma'am.
Hello, ma'am.
Yes.
Ma'am, I also have a small doubt. Can I ask?
What topic it is?
Ma'am, hypothesis testing. Ma'am, t-test and z-test, ma'am.
T-test, z-test, we just discussed sometimes.
Yes, ma'am. But ma'am, you mentioned that if the sample size is greater than 50 or equal to 50, we can use z-test instead of t-test.
50 was just one example. I mean, if the sample size is big enough, like let's say greater than 30, then the conclusion that your t-test will give will be same as the conclusion that your z-test will give. So instead of finding the t distribution value, even if you can find the probability for z distribution, it will give you the same answer, same final answer.
Okay, ma'am. Thank you.
After this session, we will upload this formula file, right?
Yeah, I will upload this formula file.
And then mock will be uploaded when?
Mock will be released tomorrow.
Okay.
Tomorrow
Ma'am.
morning, it will be released.
Ma'am, I have a couple of questions. Practice assignment 9, question number 3.
Practice assignment 9, question number 3. Okay, can we discuss the problems on Thursday session?
Okay.
Thursday session will discuss the problems if you have any. So whatever question we have from in the mock, we will take those questions, and on that basis, if any problem comes, we will take it there.
Okay.
Because it
I
will be
just-
spec wise. Yeah.
Okay. No, I just want to know if to find an unbiased estimate for variance, why do we have to divide by s square and not, but divide by n minus 1 and not n?
Yeah, because if you divide it by n minus 1, then only it becomes an unbiased estimator. We want our estimator to be unbiased. We don't
Okay.
want it to be biased. So if
So
you
if it is
find,
unbiased,
if you find the expected value of s square, where in the denominator you have n, it will not come to be equal to sigma square. Right? But if in the s square, if the denominator is n minus 1, then expected value of s square comes out to be sigma square. So this is unbiased. So this is what we want our estimator to be unbiased. So we take this to be n minus 1.
no, but then if it is unbiased, then expected value of sigma cap square will be the same as sigma square, right?
Expected value of sigma
Cap sigma hat, sigma hat square. Expected value of the
is expected value of s square will be equal
yeah,
to sigma
estimator
square.
will be the same as sigma square, right?
Yes, yes.
So if you want to calculate the expected value of the estimator, it is sigma square, correct?
Yes.
So if it is sigma square, then it is dividing by n and not n minus 1.
No. Sigma square is population variance.
Right.
S square is
Sample.
this is
Sample variance.
sample variance.
No, the question is find an unbiased estimate for variance of x. So variance of x is sigma square, right?
Variance of depends on what question. I don't know what question you have.
That's what the practice assignment question number 3.
Okay. The solution is provided, right?
Yeah, and in the solution, it is divided by n minus 1.
Find an unbiased estimate of variance of x.
So if it is an unbiased estimate, then
Here it is given that variance of x is sigma square.
Right.
And you have to find an unbiased estimate of variance of x. So unbiased estimated is s square. That is given by so what is the formula of s square? It is sum over xi minus x bar whole square divided by n minus 1.
Yeah.
So just find that and
yeah. No, but how do we know S square is an unbiased estimate of?
Yes,
yeah,
ma'am. That is my question. Also.
This we have seen before. Means
Okay.
as we have seen in week 7, week 8.
Okay.
We have seen that expected value of S square comes out to be sigma square. So it is an unbiased estimate because to check biasness, we just have to check if the expected value of estimator comes out to be the parameter. So here the parameter is sigma square and estimated is S square, and if its expected value is coming out to be the parameter, then we say it is unbiased. So S square is unbiased.
Okay. Okay, got it.
This we have seen in the previous weeks, right?
We
that
have
S square is
seen
the unbiased
week,
estimator of
week-
variance.
Week 7 we have.
Okay, okay, I must have missed it. Yeah.
Okay, okay. Right.
Okay.
Are we discussing?
I have a couple of doubts. No? Hello.
Hello.
Hello, ma'am.
Yeah.
Ma'am, I have a couple of doubts.
Okay.
Ma'am, first thing is, can we get this government exam previous semester when it was complete exam? So solve question papers, previous papers.
Previous year question paper.
Government exam solved.
You can get it from somebody. I'm sure it is already available. We are not going to provide it from our side, but you can ask somebody.
And then another one is in graded assignment 11. I have a doubt now.
Ma'am, one question. It might be silly.
Hello.
Hello.
Yeah, I'm there.
Ma'am, how important it is to solve the last year papers so that we can be sure enough that we have prepared well for this exam, interim exam. I mean, how much useful it is if we solve the last year papers?
So the last year paper also syllabus was same. Portion was okay. Portion was a little different there.
Portion was
this year we have said it is going to be 30-70.
Okay.
But last time it was not 30-70. I think it was some 40-60. I think.
Oh.
What is 30-70, madam? Like between the quizzes and this, or final exam, or what is?
Week 1 to 8 and week 9 to 12.
Okay.
Okay.
Yeah.
So it's going to be 30% for the first 8 weeks, is it?
30% of first 8 weeks this term.
This
time, and remaining 70% from Bayesian, not Bayesian, I mean estimation and hypothesis testing.
Okay.
But last time that was not the case, so I would suggest better you solve the mock properly.
Okay. Instead of solving the last year papers,
mock will be a better.
Mock will be a better solution, right?
Better, yeah. That will be better.
Can you just open there's a couple of things in the lecture. One is in the lecture and one is in the graded assignment. Can you open it now?
Sorry. Oh.
I have a couple of doubts in the week 11 lecture. There's one from lecture and one from graded assignment. Can you open it now?
Ma'am, is the today's session over? I mean, regarding accept the doubts.
Like whatever we did not discuss F test or Z test properly.
Oh, okay.
Rest of the things we have discussed.
Okay.
The problem part will be discussed in the next. Yeah.
Okay.
So there we are going to discuss the mock question. So anything around those questions that will be taken.
Are you able to hear me, ma'am? Hello.
Yeah.
Ma'am, can you just open the lecture, first lecture, 11.1. I give you the timestamp. There's slide out there. Hypothesis testing.
Can you tell me week 11?
Lecture 11.1. Yes, ma'am. In the lecture video.
Okay.
The screen, share the screen, or shall I share my screen?
You can. I don't think you can share your screen. Okay. Week 11, lecture 11.1.
11.1. Yes, ma'am. The timestamp will be around 18 minutes.
You have doubt in acceptance set. All that.
Not acceptance set. Actually, the set of probabilities calculated, but I'm not able to understand how it was done.
Okay, if you have doubt,
18 seconds, 18 minutes.
I know what the doubt is going to be, like subsets, something.
The set of values actually round about.
The next alternative.
Yeah, that's right. Yeah, right.
Yes, ma'am. There, a set of values is calculated here just below. Like if you scroll down.
I will. Yeah, no, I know what is the doubt. So.
Yes, ma'am. These values, ma'am. Yes, ma'am. It's no clue about how this was calculated. These two values, ma'am.
You can watch the first session that was done for hypothesis testing. The first session that is done for hypothesis testing, you can watch that session.
This one, right? The same one.
Sorry.
This is the first. I mean, like you're talking about your session. Right?
No. Session as in live session. Please watch the session. All that it has been discussed.
Live session of week 11.
11, first session, yeah.
Okay, so YouTube will be available on that.
It is available, yeah. So for week 11, there were so many sessions, and the topics have been covered properly.
Because I'm getting stuck here.
If you have any doubt, please refer to those sessions. There are 3 sessions conducted, overall 5 sessions. So you can watch 3 sessions and you can get many of the doubts clear.
Okay. Because basically we set the subset that is A, and then the corresponding probability was.
You can watch those sessions.
Which sessions, madam? Can you refer to the week?
Week 11, live
week 11?
session.
Live session.
Can you give us the dates, ma'am? The dates. Can you give the dates?
You go to the not calendar, the link, the playlist you have. Live session playlist.
Just Google live session playlist. Okay?
No, in your dashboard.
Okay. Dashboard. Okay. Can you just?
It will be there. Take it from there.
It is there in the supplementary contents.
Okay. It's just one more question 4, ma'am, in GA 11.
Sorry.
Question number 4 in very resonant 11.
Question number 4. I will open the solution.
The alternate hypothesis. Number 4, GA 11.
Which question?
Number 4, ma'am.
In the solution number 4?
Yes, ma'am. Solution number 4. Question number 4. See, for H0, I thought H0 is mentioned as greater than 0. It will come. Is the same question?
This one?
This is the third one.
H0 greater than 0?
Can we go to the next one, fourth one?
Okay. Not this one. Tell me the question statement.
Actually, I was looking at this question and then just made a note in my notepad. But
so I don't know which one it is.
Then could you stick to question number 2 now? Could you come down to question number 2?
Okay.
Just scroll down, scroll down. Yeah, here itself. Like here, we are not subtracting from C, right? We are subtracting only from X bar because we have taken X bar minus 10.5, right?
Because we have taken reject H0 if mod of X bar minus mu is greater than C.
Okay.
This is our test. So since we have already subtracted
Taken mu, right? Yes.
From X bar, we are not doing it again from
Yes,
C.
okay.
Anything else that you would be going with, or may I actually ask for this request of mine on method of moments again, madam?
Yeah, we'll do method of moments. Wait. Yeah, so what was the doubt here?
When we say moment, what do we mean by moment over here?
Okay, so first moment, as we had said, the first moment gives you the expected value. Right, like when we found the first moment, when we say the first moment, it gives you the expected value. When we talk about the second moment, it gives you the expected value of X square. The third moment is expected value of X cube and so on.
So what we have there is summation of X power K is
yeah. So what we have here is summation of xi to the power k, I varying from 1 to n divided by n. Okay. And this is our sample moments. This is called as sample moments. So the first moment, for the first moment, you just put k to be 1.
okay.
So that gives you sample mean.
Okay.
For the second moment, you put k to be 2.
Okay.
So it becomes x1 square plus x2 square plus up to xn square divided by n. Sorry, x1 square plus x2 square plus xn square divided by n.
Okay.
That can be that we say is expected value of x square.
So we use the second moment and subtract the first moment square, we get the variance. That is what we are going back to again?
Yes, yes. So expected value of x square is variance of x plus expected value of x whole square.
Okay.
So what we are doing is we have the distribution with us, and we know it's let's say we know its expectation. So expectation is our first moment in Angmi. So that's our expectation. So if I know
Hello, ma'am. Unable to hear you. Hello. Am I the only one? Okay.
I think she lost the connection. Get
Maya
back.
has lost the connection.
Okay.
She's frozen now. It's highly surprising, huh? We had a session on Friday and all of a sudden that has been removed. The link has been removed.
Why?
I don't know. That's what we came to know during the session. Someone said that there is no session on Friday and then we cross-checked.
No, I thought it was.
It was. I know till afternoon it was. Because when I opened my calendar today in the evening to join this session, at that time also it was there because I have
They
seen.
would have removed.
Yes, it has been removed now.
Sorry, I got disconnected.
Yes, ma'am, you got disconnected. No problem. Yes.
Was there. Yeah, so I was talking about method of movement, right? So
yes,
you have one. Let's say you have one parameter. You know its distribution mean. So you just what you do is you equate this. We say that this distribution mean is same as our first sample moment.
your screen
So the
is
first
blank.
sample.
Your screen is
Yeah,
blank.
because actually I got disconnected. Now it is all lost.
Okay.
So the first sample moment is nothing but R. And this is expected value of X.
Yeah.
We equate this to be expected value of X, distribution moment.
Right.
And from there we get our estimator for a method of moment estimator for X for the parameter.
Okay.
Similarly, if we have let's say two different parameters and we want to estimate the other parameter, then we go for, and okay, so expected value of X square,
Hello.
yeah. So expected value of X square is second moment.
Yes.
Now what we do is we know what is expected value of X square. It is mu square plus sigma square.
Yeah, mu square plus sigma square. Yes, from the variance formula. Yeah. Okay.
And we know that this expected value of X square is our M2. M2 as in sum over
1 by n
xi to the power
xi square by n.
1 by n.
Okay.
So we equate this to the variance.
Okay.
And we get our we get the second parameter. I mean the estimator for the second parameter.
Which parameter would that be, madam?
I mean, if you have two parameters, eta 1 and eta 2, then the second, then the estimator for the second parameter you get if you go for the second sample moment.
Not clear, madam. Sorry. What you on the left side is okay, but when you're talking about theta 1 and theta 2, I'm not able to follow.
Were you in the session before? I'm not sure.
I joined a little late, so
yeah. So okay, this part, right? I have explained it. Can you just go back and check once?
the part on the left is very clear. That one I understand. But
this whole this whole thing I had explained is an example also.
okay,
This
all
is
right.
normal.
Thank you.
Yeah.
Thank you.
It's
I'll
there.
go over that. Yeah, yeah.
It's already getting very late. Already
Yeah,
4
thank
hours.
you. Yeah, thank you. Good night. Thank you.
Thank you, ma'am. Thank you very much.
Yeah,
Thank you,
thank you all. We'll meet on Thursday.
Okay, thank you, ma'am. Good night.
Yeah, thank you.
Thank you, ma'am.